Hello there and welcome to Just About Earth, where curiosity slows down a little, history gets comfortable, and the past is allowed to be far more capable than we usually give it credit for. Tonight we're settling in with a subject that has a way of making modern confidence wobble just a bit. Not collapse completely, of course. Humanity still has rockets, satellites, suspension bridges, and the internet, which means we can now argue with strangers across continents in real time. But every so often we look back at something built thousands of years ago and have to admit, a little reluctantly, that there are structures in the ancient world we still struggle to fully explain, fully reproduce, or fully match on their own terms. So before we get into stone, labour, geometry, logistics, vanished techniques, and the occasional bruised ego of modern civilization, let me ask you something simple. Where are you listening from tonight? And what is the hour in your corner of the world? Maybe it's late. Maybe the room is quiet. Maybe you're listening from a city apartment with traffic still humming below, or from somewhere rural where the night feels deeper and older. There is something fitting about thinking of ancient builders in the dark. Their work survives best in stillness. In daylight, monuments can look like tourist destinations. At night, even in imagination, they return to being what they really are, statements in stone made by people who expected time to take them seriously. And if you find this kind of slow, thoughtful wandering soothing or interesting, or just a good way to let the day loosen its grip a little, I'd be very glad if you left a like and subscribed. It helps this quiet corner reach other people who enjoy science, history, and the strange comfort of realizing that human beings have always been more resourceful than they appear at first glance. Now, the idea at the center of tonight's journey sounds dramatic on purpose, and it should. Ancient civilizations built things we still can't build. That phrase tends to trigger two equal and opposite reactions. One group leans forward immediately, ready for mystery, lost knowledge, vanished giants, and perhaps a hidden chamber or two. The other group leers back with folded arms and says, well, of course we can build them. We have cranes. And the truth, as it often does, sits in the more interesting middle ground. Because in one sense, yes, modern societies can build larger things, taller things, more complex things, and certainly things with better plumbing. If an ancient Egyptian architect could visit a modern skyline, he would probably have a few questions, most of them justified. But that is not quite the point. The point is not that ancient people had secret anti-gravity machines hidden behind the temple pantry. The point is that there are structures, materials, alignments, and engineering achievements from the ancient world that remain difficult to replicate in the exact way they were done, with the exact tools they had, under the exact conditions they worked in, and with the same endurance across centuries or even millennia. That distinction matters. It matters because when people hear that we can't build something today, they often imagine a challenge of brute possibility, as if engineers around the world are standing helplessly in hard hats, defeated by a pile of rocks. But that is rarely what historians, archaeologists, or material scientists mean. What they mean is something more precise and more impressive. They mean that some ancient methods are not fully understood. Some lost materials behave in ways we still study. Some construction systems would be wildly expensive, inefficient, or socially impossible to reproduce at scale now. And some monuments, once stripped of romantic nonsense and internet mythology, are still astonishing enough on their actual merits. That might be the first thing worth clearing away before we go any further, the habit of underestimating ancient people so badly that we leave ourselves with only two choices, either dismissing them as primitive or inflating them into magic. Both are mistakes. If we assume ancient civilizations were simplistic, then every major stonework achievement begins to feel impossible. If we assume impossibility, we start inviting in fantasy. Before long, a carefully cut wall becomes evidence of space visitors, forgotten superweapons, or a global master race of mystery architects who somehow left behind no instruction manual but did leave plenty of good masonry. It is a familiar pattern. First, we underestimate real people. Then we invent impossible ones. The more honest response is usually more demanding. Ancient builders were not mystical. They were not idiots. They were people with hands, measurements, memory, discipline, social organisation, observation and time. Quite a lot of time in many cases. They worked in cultures that could direct extraordinary human energy toward a single project for decades or generations. They understood materials by repeated contact, not always by written theory. They learned what stone does when struck a certain way, what mortar does in damp air, what sun angles look like at different times of year, how ropes behave under load, how soil settles, how weight transfers, how teams coordinate, and how to make something not merely impressive for a ruler's lifetime, but stable enough to outlast empires. That is one of the difficult things for the modern imagination to sit with. We often confuse technological sophistication with electronic sophistication. If it does not involve software, steel alloys, motors, or a glowing screen, we instinctively place it lower on the ladder of achievement. But highly capable societies existed long before industrial power. They solved different problems with different constraints, and because their solutions do not look like ours, we sometimes mistake unfamiliarity for inferiority. Take stone, for example. Stone is one of the oldest building materials and one of the least forgiving. Wood can flex, metal can be welded, concrete can be poured into cooperation. Stone does not negotiate. It is heavy before you move it, awkward while you move it, and expensive the moment you make a mistake. Once shaped, it demands accuracy. Once stacked, it requires respect. Once misaligned, it tells on you for centuries. And yet ancient builders across Egypt, Mesopotamia, the Andes, the Mediterranean, the Indian subcontinent, Mesoamerica, and elsewhere, raised works in stone so durable that many modern structures already look temporary by comparison. Not all of them were massive, though mass tends to get the attention. Sometimes what survives is not merely scale, but fit. Blocks that meet so closely a blade struggles to enter the seam. Foundations that settle without catastrophic failure. Walls that endure seismic activity through shape rather than steel. Surfaces that remain smooth after centuries of weather. Drainage systems that still work. Concrete that seems to improve in certain marine conditions. Alignments that catch solstices, equinoxes, stars, shadows, or solar paths with unnerving confidence. These are not the traces of people guessing wildly and getting lucky for 1,000 years straight. And once you start noticing this, it becomes hard to stop. A wall in Peru looks almost grown from the hillside, every stone locked into its neighbour like a puzzle made by patience rather than haste. A Roman harbour structure survives wave action that destroys many modern concretes in a fraction of the time. Egyptian stonework raises questions not because it is supernatural, but because it is methodical. Megalithic sites across Europe and the Near East remind us that communal coordination itself is a form of technology. The stepwells of India reveal hydraulic understanding merged with architecture and climate response. Petra shows what happens when a city is built not only with stone, but into it. Teotihuacan, Baalbek, Sacsayhuaman, the Great Pyramid, the Pantheon, Nanmadol, Ajanta, Ellora, Derinkuyu, Sigiriya, the Long Walls, the roads of the Andes, the terraces of ancient agriculture, the reservoirs, canals, observatories and causeways of old civilizations, all present the same quiet challenge. Perhaps we have not been asking the right question. Instead of asking Rus, could we make something big now? Perhaps we should ask, could we make this exact thing by comparable means, with comparable longevity, under comparable constraints, and with the same understanding of place, material and purpose? Often, the answer becomes far less casual. There is another reason the topic deserves care. The phrase, "we still can't build," should not turn into a vague celebration of mystery for its own sake. Mystery is enjoyable, certainly. It keeps documentaries in business and late-night video thumbnails in a healthy state of exaggeration. But real historical wonder becomes stronger, not weaker, when it is grounded. It is more impressive to learn that Roman concrete may owe its durability partly to volcanic materials and specific mixing processes than to shrug and call it lost magic. It is more impressive to study how Inca masonry handled earthquakes than to wave a hand and declare it impossible. It is more impressive to reconstruct labour systems, transport methods, survey techniques, quarrying processes, seasonal timing, and political organisation than to assign the whole burden of explanation to a word like advanced and leave it floating there like a decorative cloud. What makes these ancient works remarkable is not that they violate physics. It is that they obeyed physics so well, with such limited machinery, that the results still embarrass our assumptions. There is a difference, a very important one. Ancient builders did not transcend reality. They knew it intimately. They may not have written formal equations for stress distribution in the language a modern engineer uses, but many understood load, balance, leverage, and geometry in practical terms that were good enough to keep stone overhead and water under control. In some cases, it was better than good enough. It was elegant. And if that sounds like admiration, it is. But it is not sentimental admiration. Ancient civilizations were not gentle storybook societies, living in harmony with moonlight and chisels. They could be brutal, hierarchical, exploitative, deeply unequal, and politically ruthless. Many monumental works were tied to power, religion, coercion, prestige, or imperial ambition. A building can be marvellous and still emerge from conditions we would not want to imitate. That matters too. Part of understanding how such works were made is facing the scale of organisation behind them, including labour systems that could mobilise tens of thousands of people, sometimes voluntarily, sometimes seasonally, sometimes through taxation, conscription, or force. In other words, one answer to the question of why we do not simply recreate some of these structures today is that we often do not live in societies willing to spend that much time, labour, money, or political capital on the same kinds of projects for the same reasons, using the same methods. When modern engineers say something is possible, they usually mean technically feasible within a framework of current costs, regulations, expectations, supply chains, labour laws, and deadlines. Ancient monumental building often lived in another world entirely, one where the monument itself could become a state priority, a religious necessity, or a ruler's claim to permanence. That can be difficult to grasp because modern life trains us to think in short cycles, quarterly results, election cycles, construction schedules, shipping estimates, 2-day delivery if everything behaves. Ancient monuments often belong to longer rhythms, decades of quarrying, generations of expansion, maintenance across dynasties, the expectation that work began before you and would continue after you. If you build that way, you build differently. You choose different materials. You tolerate different timelines. You train craftsmen differently. You make peace with slowness, and slowness, inconvenient though it is, can produce astonishing things. There is also the question of memory. Not everything ancient builders knew was written down, and not everything written down survived. Skill can exist in the hands as much as in the text. A master mason can know things difficult to translate into words. A quarry worker can hear stress in stone. A plasterer can judge mixture by touch. A builder can sense alignment through repeated practice long before precision instruments exist in portable form. If such traditions break, the result is not just lost information, but lost habits of perception. And then centuries later, modern observers arrive and say, how did they do this? Sometimes because the answer is gone, and sometimes because the answer was always more physical, distributed and experience-based than we expect from knowledge. By now, you can probably feel the shape of the subject taking form. This is not going to be a parade of exaggerated claims about impossible monuments made by people who apparently had no business being competent. It is something much more useful than that. It is a careful look at what ancient civilizations achieved, why certain things remain so hard to match, and what those achievements tell us about labour, intelligence, patience, materials, and the danger of assuming history moves in one straight line from primitive to advanced. Because it doesn't. Knowledge can accumulate, yes. It can also scatter. Techniques can be refined, forgotten, replaced, rediscovered, or rendered uneconomical. Materials can fall out of use. Entire building philosophies can vanish when the society supporting them collapse. What survives may not be the best method in every absolute sense, but the method best suited to a particular world. We do not build Roman harbours because we are incapable of mixing wet stuff and putting it near water. We do not build pyramids because skyscrapers are easier for housing and commerce. We do not organise massive stone-lifting societies because modern priorities are elsewhere, and because people tend to object quite reasonably when told they must spend 30 years hauling limestone for someone else's afterlife plan. Still, the monuments remain, and they do something very inconvenient to modern vanity. They force us to admit that progress is not one simple staircase. A civilization may know less than we do in some domains and more than we do in others. It may lack engines but possess astonishing surveying accuracy. It may lack steel cranes but command enormous labour discipline. It may not have digital modelling but understand local geology so well that its foundations behave beautifully for centuries. It may not define chemistry the way we do, and yet produce a concrete or pigment or metal treatment whose performance still invites analysis. There is a humbling pleasure in that. At least there should be. The past does not need our pity. It needs our attention. And the more attention we give it, the more the old caricature falls apart. Ancient builders were not standing around waiting for modern people to arrive and explain triangles. They were making states, roads, tombs, temples, canals, fortifications, observatories, terraces, water systems, and urban plans with the means available to them, often with an effectiveness that lasted far beyond the careers of those who commissioned them. So tonight, and in the stretch ahead, we're going to take this slowly. We'll look at the giant stones and the fine joints, the alignments and the logistics, the carved mountainsides and the engineered waterscapes, the materials that endured and the methods that disappeared. We'll separate what is genuinely unresolved from what is merely inconveniently impressive. We'll keep the wonder, but we'll keep the evidence too. And as the picture sharpens, something else begins to happen. The monuments stop looking like isolated miracles and start looking like the visible tips of entire civilizations that trained people, organised labour, moved resources, watched the sky, measured the land, and built with a seriousness we still recognise. Because before we can understand the walls, the platforms, the vaults, the roads, the terraces, and the enormous blocks that still leave modern visitors staring upward with that very specific mixture of admiration and confusion, we have to spend a little time with the people behind them. Not as mythic geniuses, not as helpless primitives, just as builders, in the fullest sense of the word, working inside societies that expected stone to carry memory, authority and belief long after the hands that placed it were gone. And once you begin there, the monuments start to look less like puzzles dropped from nowhere, and more like the logical, disciplined outcome of cultures that built as if time itself were part of the design. What made these civilizations so capable was not only what they built, but the kind of people they became in order to build it. Monuments have a way of stealing all the attention. A visitor stands before a pyramid, a fortress wall, a rock-cut temple, a terrace system, or a vaulted dome, and the mind goes straight to the finished object. It is a very natural reaction. Finished things are dramatic. They sit there with the confidence of a completed sentence, but the finished object is only the visible part of a much larger story. Behind every massive block, every aligned corridor, every polished stone face, Every engineered slope and carefully measured foundation, there were generations of builders who had learned how to see the world in a very specific way. That is one of the easiest things to forget when looking at the ancient world from a comfortable modern distance. We tend to imagine individual brilliance because it is tidy. We like the idea of a master genius pointing somewhere and saying, "Put the wall there," and then history taking care of the rest. Real building, especially on the ancient scale, is almost never that neat. It depends on systems of training, habits of attention, shared techniques, repeated mistakes, accumulated corrections, and large numbers of people who know exactly what their hands are doing. A monument may bear the name of a ruler, but rulers are rarely the ones hauling, measuring, shaping, lifting, aligning, draining, smoothing, or adjusting. They may want immortality, certainly. Many did. But immortality, rather inconveniently for them, usually required skilled workers with sore backs and very practical minds. When we say that ancient builders worked beyond their age, it does not mean they somehow escaped history and wandered into a future they did not belong to. It means that their capabilities often exceeded the assumptions later societies made about them. They were operating at levels of competence, organisation, and technical sensitivity that do not fit the lazy picture of antiquity as a long prelude to real knowledge. In truth, many ancient societies were not stumbling towards civilization. They were civilized already, and often in ways that demanded high precision, strong institutional memory, and an ability to coordinate labour on a scale that remains impressive even now. Consider what it means to shape stone well. Not just hit it until it becomes vaguely rectangular, but work it to a desired plane, a fit, an angle, a curvature, a tolerance. That is not random force. That is trained judgment. A stonecutter does not need a degree in material science to understand grain, fracture, pressure, and resistance. Repeated contact teaches lessons no textbook can fully replace. One strike is too hard, another too soft. One angle opens the stone, another ruins it. A surface that looks flat from a distance may fail completely when brought against its mate. Now multiply that knowledge across teams, quarries, generations, and cultures. Multiply it again when the work involves transport, lifting, fitting, and long-term stability. What begins to emerge is not a miracle, but a profession. And professions matter. An ancient civilization capable of monumental construction was not merely rich in labour, it was rich in practice specialisation. Somewhere in that society were surveyors, planners, overseers, quarry workers, transport crews, rope makers, tool makers, scribes, foremen, water managers, carpenters, plasterers, and masons who had spent years learning what not to do. Which, as anyone who has ever attempted home improvement for the first time already knows, is often the most valuable part. The history of building is, to a surprising degree, the history of making fewer catastrophic mistakes on purpose. This is why the phrase, "they had only simple tools," can be so misleading. Simple compared to what? Exactly. Compared to laser cutters and tower cranes, yes. But a tool is never just an object. It is an object plus the technique behind it. A copper chisel in untrained hands is a poor thing. A copper chisel in skilled hands, used with abrasives, leverage, rhythm, and support from a whole working system, becomes part of a process capable of remarkable results. The same is true of plumb lines, levelling devices, wooden sledges, rollers in certain contexts, levers, cords, stakes, hammers, wedges, water trenches, earthen ramps, and all the other low-glamour technologies that do not look impressive in isolation, and yet quietly make civilization possible. Modern people sometimes suffer from an unfortunate weakness for dramatic machinery. If it does not roar, rotate, emit sparks, or require a warning label, we are tempted to think it cannot be doing serious work. Ancient builders would likely find this funny, though perhaps not in a charitable way. They understood something fundamental: technique scales. A good method, repeated patiently by many people, can outperform a more advanced method applied carelessly. A well-organised labour force with ordinary tools may achieve what a poorly organised one with better tools cannot. Precision, in other words, is not only a property of equipment, it is also a property of culture. That cultural dimension is easy to miss because it does not survive in the same way stone survives. We can stand before a wall and admire the wall. We cannot stand before the apprenticeship system that trained the people who made it. We do not see the years of observation, the repetition of craft, the correction by older hands, the inherited rules of thumb, the seasonal knowledge, the division of labour, the routines for checking alignment, the practical mathematics, the shared vocabulary of materials. Those things vanish more easily, and yet they may be the real reason the wall exists at all. In societies that built on an enormous scale, skill was often social before it was individual. A worker knew his task, but he also knew where his task fit within a chain. The quarry crew had to produce what transport crews could move. Transport crews had to deliver what masons could place. The masons had to trust that the foundation team had prepared correctly. The people mixing mortar or preparing bedding surfaces had to work in a rhythm that suited placement. Surveyors had to establish lines others believed in. A single structure might require thousands of acts of coordination, many of them unrecorded, many of them routine, many of them so well practiced that they left no dramatic story behind. History tends to remember the king. The building remembers everyone else. There is also a tendency to imagine ancient labour as little more than brute force arranged in rows. Brute force was certainly involved. One does not move multi-ton stones by asking politely, but force without planning is just expensive chaos. The larger the project, the more intelligence must be built into its logistics. Food has to arrive, tools have to be maintained, pathways have to be cleared, materials must be staged in the right order, sledges break, ropes fray, workers fall ill, weather interferes, foundations shift, measurements need repeating. If the structure is aligned to celestial events, then timing matters in more ways than one. If the work is tied to flood cycles, seasonal labour availability, or political ceremonies, the schedule becomes even more complex. Ancient monumental building was not only hard because stones were heavy, it was hard because keeping thousands of people and processes synchronized over long periods is one of the most difficult things any society can do. That is where administrative sophistication enters the picture. You cannot sustain enormous building campaigns without records, redistribution, and command systems. Ancient Egypt is a useful example, not because it was uniquely capable, but because it makes the point so clearly. The Great Pyramid Age did not emerge from a desert full of enthusiastic amateurs who happened to have a free weekend. It emerged from a state with agricultural surplus, taxation, labour organisation, quarrying networks, transport infrastructure, religious motivation, political centralisation, and enough administrative muscle to feed, house, and direct large numbers of workers. The monument is spectacular, yes, but the bureaucracy behind it is almost as impressive, even if considerably less photogenic. And that is another quiet truth about ancient builders. They were often working inside systems that valued continuity more than novelty. Modern culture likes invention, disruption, reinvention, and whatever else can be marketed with dramatic music. Ancient monumental cultures often prize transmission. A method proven to work could be preserved, refined, ritualized, and repeated across generations. That creates a different relationship to craft. A modern builder may learn a new software package every few years. An ancient builder might learn a sequence of practices anchored in lineage, locality, and accumulated trust. There are strengths and weaknesses in both models, of course, but one advantage of the older model is depth. If the same craft traditions are sustained for long enough, a society can become extraordinarily good at specific forms of building. This helps explain why certain achievements seem to arrive not as isolated sparks, but as clustered periods of excellence. Once training, institutions, labour systems, and material knowledge align, A civilization can produce wave after wave of works that share a family resemblance of competence. It is not that one miracle happened and everyone else spent centuries looking puzzled. It is that a whole environment of skill became possible. Egyptian stone architecture, Roman concrete and vaulting, Inca masonry and terrace engineering, Nabatean hydraulic management, South Asian rock-cut architecture, Mesoamerican urban planning, and many other traditions make more sense when seen as ecosystems of knowledge rather than one-off acts of brilliance. That ecosystem included memory in forms we do not always respect enough. Not everything important is written in abstract principle. Some of it lives in process. A builder learns by watching how a senior mason judges a seam. A quarry master learns where to cut by seeing where the stone wants to open. A team learns how many people to assign to a drag, how wet to make the path, how to brace a load on a slope, how to set a block so it can still be nudged once lowered. These things may be partially verbalized, but they are often embodied, which means that when a civilization falls, or when patronage shifts, or when conquest interrupts training chains, knowledge can disappear without ever being dramatically lost in the romantic sense. It simply stops being practiced. A few centuries later, people stand before the surviving work and wonder where the secret went. Sometimes the secret went nowhere. It just died with the workflow. This is one reason ancient building can still feel uncanny. We are often comparing a surviving object to an absent process. The object remains. The people, workshops, institutions, and repeated routines that produced it do not. That imbalance makes the accomplishment look more mysterious than it may have felt to those inside the tradition. A Roman builder working under a practiced system of concrete mixing, pozzolanic materials, formwork, arches, and labour management might not have considered himself a magician. He might simply have considered himself busy. It is later generations, missing the chain of ordinary competence behind the extraordinary result, who start to treat the structure as though it arrived by revelation. Even the pace of ancient work matters here. Many large projects unfolded over spans of time that would make modern developers lie down in a dark room. Years of preparation, decades of execution, adjustments across reigns, additions by successors, repair and refinement as standard practice. When speed is not the supreme value, different standards become possible. Stones can be dressed more carefully. Settlement can be observed. Finishes can be revised. Teams can specialise without being rushed into the sort of regrettable compromise modern buildings occasionally advertise by leaking at the first sign of weather. This is not to say all ancient work was flawless. Some of it failed. Some of it cracked. Some grand projects remained unfinished. Ancient people were very capable of making a mess. But when their systems worked well, they were capable of a patience that modern construction culture does not often reward. There is also the matter of intention. Many ancient builders were not working merely to enclose space efficiently. They were making things meant to embody order, power, continuity, sacredness, or cosmic relationship. That affects choices. If a structure is meant to mirror the heavens, mark a ruler's legitimacy, house the dead forever, frame ritual movement, or materialize an empire's reach, good enough becomes a very different standard. Societies will spend astonishing amounts of labour when the object in question is not just useful, but meaningful. A monument can be an argument made in stone. It can say that the state commands labour, that the gods are honoured, that time has been mastered, that chaos has been pushed back, that this ruler belongs in a line older than memory. Under those conditions, precision is not vanity. It is ideology with measuring cords. This is why the builders themselves deserve more attention than they usually get. They were not just workers executing orders. They were the practical intelligence through which a civilization converted belief into structure. A ruler may demand a tomb aligned to the cardinal directions. Fine, someone still has to make that alignment real on the ground. Priests may insist on ceremonial pathways, symbolic dimensions, or celestial correspondences. Fine again. Someone must still quarry, level, fit, lift, and finish. The distance between concept and monument is filled by people whose names are mostly gone, and whose competence remains visible every time one of those structures catches the morning light or survives another rainy season. And occasionally, if we are lucky, history lets some of them come into view. Graffiti from workers' crews, records of wages, quarry marks, construction notes, remains of settlements built to house labourers, evidence of diet and injury, signatures from stonemasons, the traces of administration that remind us these were not anonymous swarms but organised human communities, sometimes well-fed, sometimes overworked, sometimes proud, sometimes coerced, often skilled. The reality is usually more human and more complicated than either romantic admiration or cynical dismissal allows. It is also worth noticing that ancient builders were rarely working in ignorance of the natural world around them. They watched terrain, water, seasonal change, local geology, and the behaviour of materials with a seriousness that practical life required. A terrace system built into a mountain slope is not just architecture. It is hydrology, agriculture, soil management, and slope stabilisation. A temple platform is not just a ceremonial base, it is also a foundation problem. A harbour is not only a commercial asset, it is a negotiation with wave energy, sediment, and corrosion. Ancient builders learned from environment because failure was expensive and often public. A badly built wall embarrasses a household. A badly built state monument embarrasses a civilization, which tends to focus the mind wonderfully. All of this should make us more careful with the word primitive. It is a word that has damaged a great deal of thinking. It encourages the fantasy that history is a simple upward climb, in which earlier people are automatically less perceptive, less systematic, and less capable. In reality, capability is uneven. A society can be advanced in one domain and limited in another. It can possess astonishing craft traditions and poor sanitation, impressive astronomy and harsh labour systems, elegant hydraulic works and brutal politics. The ancient world was not lesser because it was earlier. It was different, and in certain areas it reached levels of mastery modern people ignore at their own intellectual expense. If anything, the builders of the ancient world force us to widen our idea of intelligence. Intelligence is not only theory formalized on paper, it is also sequencing, repetition, feel, observation, adaptation, and the ability to make reliable things under difficult constraints. It is training enough people well enough that the quality holds across a project too large for any one person to oversee directly. It is knowing when to follow the plan and when the stone, the slope, the weather, or the load requires a change. It is recognizing that a civilization is only as durable as its ability to transmit competence. And once you begin to see ancient builders this way, something shifts. The monuments stop appearing as isolated wonders and start looking like evidence of long-disciplined societies. The mystery does not vanish, but it becomes sharper and more respectful. Instead of asking what supernatural trick explains the result, you begin asking what forms of training, organization, and material understanding made the result normal enough to achieve. That question leads somewhere better. It leads toward quarries, workshops, labour camps, apprenticeship chains, seasonal schedules, and methods so grounded they can still humble modern observers who arrive expecting a simpler past. Because the real surprise is not that ancient civilizations built extraordinary things once in a while. The real surprise is how often they did it, how consistently, and how much of that consistency depended on builders who were operating with a depth of skill their age is rarely credited for. And once that becomes clear, the stones themselves start to look different. Heavier, certainly, more deliberate, less like mute relics and more like the final, visible surface of an entire world of knowledge working underneath them, which is where the story becomes even more interesting, especially when those builders turn from skill alone to the problem of size. There is a particular kind of silence that happens when a person first stands in front of a truly enormous stone from the ancient world. Not a dramatic silence, not the sort film directors like to fill with swelling music and someone whispering the word impossible. It is quieter than that, more practical. The mind begins by doing what it always does with large objects. It tries to estimate height, width, thickness, mass. It starts comparing a car, a room, a truck, a house. Then the comparisons fail, or at least they stop being satisfying, because the problem is not simply that the stone is large. The problem is that the stone is there at all, in the place where ancient people somehow got it, shaped it, lifted it, aligned it, and left it so securely that centuries later we're still standing nearby, trying not to look too confused. That reaction is one of the most reliable clues that we're dealing with a real achievement rather than a romantic exaggeration. Ancient civilizations built plenty of beautiful things. Beauty impresses us in one way. Vast stone impresses us in another. Vast stone demands explanation. It invites engineering questions almost against your will. Where was it quarried? How far did it travel? What path did it take? How many people were needed? What kind of tools shaped it? How was it lifted or lowered? How precisely did it need to be placed? What happened when something went wrong? Most importantly, how did the people responsible understand the difference between what was difficult and what was impossible? Because it is one thing to move a heavy stone badly. Human beings, when motivated enough, can drag alarming things for no good reason at all. It is another thing to move heavy stone intentionally, repeatedly, and as part of a planned building system. This is where some of the most famous megalithic sites in the world still have a way of unsettling modern confidence. Not because they are supernatural, and not because historians know nothing, but because the scale involved pushes every explanation into a more demanding territory. Ordinary words begin to feel unhelpful. We say transport, but transport can mean a person carrying a basket, or a society moving a block that weighs hundreds of tons. We say quarrying, but quarrying can mean shaping decorative stone, or detaching a giant monolith without ruining it before it even begins its journey. We say lifting, but lifting can mean nudging into place or raising something so heavy that any serious mistake turns labour into disaster. Take Baalbek in present-day Lebanon, where some of the largest known stones ever quarried in antiquity still sit as a standing challenge to anyone inclined to underestimate Roman engineering or the local traditions that preceded and supported it. The site is famous for many reasons, but one detail in particular tends to interrupt conversation. The Temple of Jupiter platform includes massive foundation stones, and nearby in the quarry lie even larger unfinished monoliths, among them blocks so huge that even modern observers, very much accustomed to cranes and industrial hauling, do a double take. The famous trilithon stones built into the podium are each estimated at around 800 tons or more, while some quarry stones exceed even that by a considerable margin. One unfinished block, often called the Stone of the Pregnant Woman, is enormous enough on its own to make every sentence around it sound slightly inadequate. Another even larger monolith has been identified in the quarry area. These are not decorative slabs. These are serious acts of stone ambition. Now, it is important not to drift into the easy mistake of turning difficulty into mystery theatre. Baalbek does not require aliens, levitation, or secret anti-gravity monks operating under a moonless sky. It requires something both less glamorous and far more impressive. A society willing and able to cut, prepare, transport and position enormous stones using manpower, engineering judgment, earthworks, rollers or sledges in some combination, levers, ropes, and careful control of gradients. But saying that out loud does not remove the force of the question. It sharpens it. Because once you reject fantasy, you are left with the real magnitude of what had to be managed. Ancient builders did not solve the problem by magic. They solved it by understanding force, friction, balance, and organisation well enough to make the impossible look merely very difficult. and that is often the threshold where modern people become uncomfortable. We are happy to admire the finished result in a general sense. What unsettles us is the practical sequence. If a block weighs 800 tons or 1,000 or more, then every part of the process becomes unforgiving. The quarry cut must be accurate enough that the block separates cleanly. The route from quarry to site must be passable, graded or prepared. Supporting timbers, sledges or hauling frameworks must endure enormous stress. Ropes must hold. Ground conditions must be managed. The destination platform must be ready. Placement must be controlled. Momentum, that usually helpful companion in smaller tasks, becomes a dangerous idiot when mass grows too large. Once something that heavy begins doing the wrong thing, persuasion is no longer an option. Baalbek is not alone in this. Egypt, of course, enters the conversation almost immediately, because Egypt has an irritating habit of remaining relevant whenever ancient stone scale is discussed. The pyramids are the best-known example, but even beyond them, Egyptian building culture repeatedly demonstrates a willingness to treat gigantic stone as a normal administrative problem. Obelisks provide a particularly revealing case. An obelisk is not merely a tall stone. It is a tall stone that must be quarried as a single piece, shaped, transported, raised upright, and survive the experience without catastrophic cracking. The unfinished obelisk at Aswan is one of the most instructive objects in the ancient world because it lets us catch the process mid-failure. Still attached to the bedrock by the moment of its abandonment, it shows the scale of Egyptian intention with unusual honesty. If completed, it would have been the largest known obelisk ever erected. It also shows something equally important. Ancient builders were not infallible. They attempted extreme things and sometimes lost the stone. That does not diminish their ability. It makes it more credible. Credibility matters here, because people often imagine the ancient world in two unsatisfying extremes. Either every monument was produced with easy certainty by civilizations of flawless competence, or else every large stone becomes an unsolved riddle beyond human explanation. Neither picture is useful. The truth is better. Ancient builders understood enough to attempt bold operations, sometimes succeeded brilliantly, and sometimes hit the limits of material behaviour. A crack in a quarry is not evidence of ignorance. It is evidence that they were operating near the edge of what their tools and methods could reliably control. The Great Pyramid at Giza offers a different version of the same problem. Much of the stone used there is not in the 1,000-ton class of Baalbek, but that does not make the accomplishment simple. Scale is not only about the heaviest unit, it is also about the number of units, the accuracy of placement, the levelling of the site, the organisation of quarrying, transport, ramp systems, internal passages, casing stones, and the administrative rhythm required to sustain the work. Tens of thousands of labourers were not all doing the same job at once, and that matters. A pyramid is not a pile. It is a managed geometry. Even more irritatingly for those who want the past to look clumsy, many of the tolerances involved remain impressive. The base levelling, cardinal alignment, and overall execution do not suggest a culture guessing with stones until the shape looked about right. They suggest systems of measurement and correction strong enough to maintain order over an enormous project. And then there are the granite elements, particularly in chambers and structural components where the difficulty changes character. Limestone is one challenge, granite is another. Hard stone resists both extraction and finishing. It demands patience, abrasives, repeated labour, and tool strategies matched to material. This is where people sometimes lapse into exaggerated claims, insisting that because ancient tools were limited, the results must be impossible. But hard material does not become unworkable simply because the process is slow. It becomes expensive in labour. Ancient states, under the right conditions, had labour to spend. What modern observers often underestimate is not what can be done with modest tools, but what can be done with modest tools used systematically for a very long time. Still, some stones remain genuinely startling even when one understands the general principles. The polygonal masonry of the Andes, especially in sites associated with the Inca and earlier cultures, offers another kind of challenge. Here the issue is not always absolute tonnage, though some blocks are very large indeed. The issue is fit, interlock, and seismic performance. At places like Sacsayhuaman above Cusco, walls composed of massive stones joined together in irregular patterns so tight and stable that they continue to provoke admiration from engineers, masons, and anyone with functioning eyesight. Some of the blocks are huge, shaped into complex forms, and fitted without mortar in ways that help the walls respond to earthquakes. One does not need to invent laser cutting to appreciate the difficulty. The challenge lies partly in shaping stones to meet each other across multiple surfaces while maintaining stability and desired wall lines. It is a kind of practical geometry learned in stone rather than on paper. Once again, what defies explanation is not the broad physical principle. People can shape stone. People can test fit. People can remove high points. People can adjust. The real challenge is the amount of skill, time, and repeated checking required to do it at scale and with such reliability. A single tight-fitting joint is an achievement. A whole wall of them, built from stones that are large enough to make your knees suddenly interested in safety, is something else. And if you have ever tried to fit even two poorly cut pieces of furniture together after a long day, the achievement becomes more personal than academic. Stonehenge represents a different form of megalithic difficulty. The stones there are smaller than the giants of Baalbek, but the project remains instructive because it combines transport, erection, shaping, and alignment across a landscape. Some stones came from considerable distances. The blue stones in particular have generated years of debate regarding exactly how much of their journey was managed by humans directly, how much was aided by natural glacial transport before human reuse, and what routes or methods were involved in final placement. Here the explanation is not absent. It is contested, refined, and in some parts incomplete. That distinction is important. Ancient stonework often defies explanation not because no explanation exists, but because the exact sequence of operations cannot always be reconstructed with full confidence. Archaeology is good at narrowing possibilities. It is not a time machine equipped with project logs and a cheerful foreman. That missing procedural detail is part of what keeps these stones so powerful. We see endpoints. We see tool marks sometimes, quarry traces sometimes, unfinished attempts sometimes, wear patterns sometimes. From these fragments, archaeologists build models. Experimental archaeologists drag replicas on sledges, raise test stones with ropes and frames, test friction, study soil, calculate labour force size, and compare what the body can really do when many bodies work together. This work is extremely useful and usually much less glamorous than internet mythology. It rarely produces a single cinematic answer. Instead, it shows that several methods might be plausible, that ancient operations were often hybrids, and that much depended on local terrain, seasonal timing, available timber, lubrication of surfaces, slope control, and the difference between theoretical possibility and repeatable practice. This is why really large stones remain such an intellectual test. They force explanation to become specific. It is not enough to say they used ramps. What kind of ramps? Built from what? With what gradient? For what stage of transport? Removed how? Stabilized how? It is not enough to say they used manpower. How many people? In what arrangement? Pulling with what harness system? Resting at what intervals? Coordinated by what signals? Supported by what logistics? It is not enough to say they had rollers. Rollers work in some contexts and fail badly in others. It is not enough to say they used levers. Levers are wonderful right up until the load exceeds what the setup can tolerate, or the stone behaves in a way the theory did not politely mention. The same difficulty appears in places like the Western Wall tunnels in Jerusalem, where some foundation stones are immense, or in megalithic works in the Mediterranean and Near East, or in certain Indian temple complexes where monolithic elements, raise their own sequence of quarrying and lifting questions. In each case, the basic ingredients recur: stone, labour, tools, planning, earth, wood, rope, time. That sounds manageable until the numbers grow large enough to expose how little room for error there really was, and perhaps that is the most interesting thing about giant ancient stones. They are not just evidence of strength, they are evidence of restraint. To move a huge stone successfully, one must resist the temptation to rush. Every stage requires control. Quarry too aggressively and the block fractures. Drag too fast and the load destabilizes. Lower too carelessly, and months of work end in one unforgiving sound. The stone teaches patience because the stone does not care how important the ruler is or how impressive the ceremony will be once it is in place. Gravity is refreshingly indifferent to prestige. This also helps explain why some very large stones were abandoned. The archaeological record includes unfinished monoliths, partially detached blocks, and projects that seem to have been halted. These are not embarrassments to ancient engineering. They are some of its most useful witnesses. They show intention before completion, method before myth. An unfinished giant in a quarry tells us what builders thought was possible, what scale they were willing to attempt, and where material reality sometimes pushed back. In a way, unfinished stones are kinder to historians than finished monuments, because they freeze the work in an exposed state. They leave clues the completed structure hides. Another reason these stones still feel difficult to explain is that modern construction rarely chooses to solve problems in the same way. If we wanted a massive platform today, we would likely not quarry and move the largest monoliths possible unless there were a very specific reason to do so, and someone else had agreed to fund the resulting headache. We would break tasks into smaller units, use reinforced concrete, use steel, use modular systems, use cranes and heavy transport vehicles. In other words, modern engineering often avoids the exact challenge ancient megalithic building embraced. This can create a strange illusion. Because we do not usually build that way now, the old method starts to look not merely old, but inexplicable. Yet in some cases it is not that we cannot understand the physics, it is that we no longer live in systems where this was the preferred solution. Preference, however, does not erase achievement. A society that chooses to move a giant stone when smaller stones would be easier is making a statement. Sometimes the statement is political, sometimes religious, sometimes aesthetic, sometimes structural, often all four at once. The stone becomes proof of command over labour, proof of seriousness, proof that the builder belongs to a scale larger than ordinary life. That is why giant stones tend to appear in sacred, royal, or strongly ceremonial contexts. No one drags an 800-ton block uphill because they have run out of sensible hobbies. They do it because the finished object is meant to communicate power in the most literal terms possible. And power communicated through stone has one enormous advantage over power communicated through speeches. The stone remains, regimes fall, languages shift, priests disappear, roads change. The block stays where it was placed and continues making the same argument. We were organised, we had labour, we understood material, we could command time, we could make weight obey intention. A giant stone is not subtle, that is part of its success. Even so, there is a danger in talking about these monuments only in the language of awe. Awe is deserved, but awe can flatten detail. Once every giant block becomes mysterious, the real distinctions vanish. Some sites challenge us because of mass, others because of fit, others because of transport distance, others because of the height at which stones were placed, others because of the environment in which they survive, others because the written and archaeological record leaves key steps uncertain. Keeping those differences in view makes the ancient world more impressive, not less. It reminds us that megalithic achievement was not one trick repeated everywhere. It was many different solutions, invented by different cultures for different reasons, each one shaped by local material, terrain, labour systems, and symbolic needs. So when we say these stones still defy explanation, the most honest version of that statement is not that explanation has failed completely. It is that the full practical sequence is often partly missing, and the remaining possibilities are demanding enough to keep experts arguing. That is a healthy sign. It means the achievements are real enough that they withstand lazy summaries. It means the stones are still doing what they were always meant to do, which is force the people standing near them to adjust their sense of scale. And once you begin adjusting that scale, other questions naturally follow. Not only how ancient civilizations moved massive stone, but how they shaped it so precisely when the tools seemed too modest for the result. Because weight is only half the story. A giant block can be moved badly. What makes many ancient sites more unsettling in the best possible way is what happened after the stone arrived. When the task shifted from force to accuracy, and the builders had to prove they understood not just how to conquer size, but how to control it. If giant stones force us to ask how ancient builders managed weight, precision forces a different and in some ways more unsettling question. How did they manage accuracy? Moving a large block is one kind of problem. Putting that block exactly where it needs to go, at the right angle, on the right line, with the right fit, and doing so again and again without steel frames, laser levels, computer models, or machine-cut standardization is another. Weight gets attention because it is obvious. Precision is quieter. It does not always impress from a postcard. It reveals itself slowly in alignments, joints, surfaces, symmetries, gradients, curves, and tolerances that make modern people lean in a little closer and realize they may have arrived with the wrong assumptions. There is a habit, especially in popular imagination, of treating precision as if it belongs automatically to modernity. If something is straight, smooth, aligned, or geometrically disciplined, the mind reaches for advanced instruments. That instinct makes sense. We live in a world full of machine-made regularity. We trust factory tolerances, digital layout tools, GPS coordinates, prefabricated parts, and measuring devices so accurate they can make an ordinary person feel slightly inadequate for eyeballing a bookshelf. But ancient builders were not working in a world without precision. They were working in a world where precision had to be produced differently. That difference matters. It changes not only the methods, but the culture around building. Because precision in the ancient world was rarely the result of one miraculous tool. It was usually the result of systems. Systems of measurement, systems of training, systems of repeated checking, systems of correcting small errors before they became large ones. A plumb line is simple, a measuring cord is simple, a set square is simple, a water level in its basic form is simple. None of these devices look particularly dramatic. None would impress anyone at a technology expo. And yet, when combined with disciplined procedure, stable reference points, good geometry, and people who understand what they are looking at, they become enough to produce results that still hold up under scrutiny. The first thing ancient builders understood, perhaps better than many of us do now, is that precision begins long before the final placement of stone. It begins with establishing reference. A line must mean something. A level must remain level. A corner must be checked against a broader plan. Distances must be transferred reliably. If a building is meant to align with cardinal directions, solar events, a ritual axis, or the slope of the terrain, that alignment must be built into the earlier stages, not admired later as a happy accident. Ancient builders did not wait until the monument was nearly done, and then casually ask whether it seemed a little off to the left. This is why survey work is so important in understanding ancient precision. Before a stone is shaped, before a wall rises, before a foundation trench is cut, somebody has to define the space. In Egypt, in Mesopotamia, in the Roman world, in the Andes, in Mesoamerica, in South Asia, and elsewhere, builders developed ways to impose order on land with tools that were limited in material complexity, but strong in practical logic. Stakes, cords, sighting poles, weighted lines, levelling trenches, and careful astronomical observation could create reliable frameworks. Not because they were magical, but because geometry is wonderfully democratic. It does not require electricity. It only requires that someone understand it and care enough to apply it properly. And the ancient world cared a great deal. In some cultures, alignment was more than technical. It was symbolic. A temple orientation might bind architecture to the rising sun. A pyramid's placement might express cosmic order. A city grid could reflect political control as much as urban planning. Once precision becomes meaningful in religious or state terms, it stops being merely practical. It becomes part of legitimacy. That tends to improve attention to detail. A ruler may tolerate many things. Public cosmic incompetence is usually not among them. The Great Pyramid is the obvious example, because it remains almost annoyingly useful. Its alignment to the cardinal directions has long drawn attention, and rightly so. However the exact methods were carried out in practice, the result was not casual. It required observation, method, and correction. Ancient Egyptian surveyors likely used stellar observations, sighting techniques, and chord-based layouts to establish orientation with remarkable care. No lasers were involved, no satellites hovered helpfully overhead. Just sky, instruments of startling simplicity, repeated human checking, and enough procedural discipline to turn broad intention into measurable result. The point is not that the ancients somehow possessed hidden modern devices. The point is that good geometry, patiently executed, can do a great deal more than modern arrogance likes to admit. The same principle appears in levelling. Large structures do not forgive bad foundations. If you are building something enormous, tiny errors at the base grow into larger errors as the work rises. Modern builders solve this with a variety of instruments and machines. Ancient builders solved it with slower but still effective methods. Water, for one, is famously uninterested in human excuses. It finds level without consulting anyone's opinion. Water-filled trenches, channels, or vessels could serve as reference systems. Combined with stakes and measured transfers, they allowed builders to create surprisingly accurate baselines over large areas. Again, the underlying science is straightforward. What is impressive is the reliability with which it could be applied across major projects. And then there is stone shaping, where ancient precision begins to look less like abstract geometry, and more like a very long conversation between hand, tool, and material. Because when modern people hear that ancient workers lacked hardened steel cutting systems or machine saws, they often leap immediately to the conclusion that fine stonework must therefore be impossible. This usually says more about our own relationship to craft than theirs. We tend to assume that if a process is slow, it cannot be accurate. Ancient builders knew better. Slow can be exact. Slow can be corrective. Slow can remove one small imperfection at a time until a fit emerges that seems almost unreasonable in retrospect. Hard stone could be worked using combinations of pounding, pecking, abrasion, drilling, chiseling where appropriate, and repeated surface checking. Copper, bronze, stone pounders, wooden tools, sand abrasives, and water could all play roles depending on the culture, period, and material involved. Harder stones often demanded less cutting in the modern sense, and more wearing down, rubbing, grinding, and shaping through persistence. It is not the kind of labour that photographs well, which may explain why people are so eager to replace it with fantasy. But fantasy is less impressive than patience when patience actually works. Look at finely fitted masonry in Egypt or the Andes and one fact becomes unavoidable. Ancient builders did not need every tool to be harder than the final stone, in the same way modern cutting tools often are. They needed a working process that could gradually refine form. Abrasives do the real cutting in many contexts. The tool can guide, pressure, or hold while the abrasive wears the material. Repetition takes the place of speed. Templates and test fitting take the place of computer previews. Human hands become part of the measuring system. It is labour-intensive, yes, but labour intensity is not evidence of impossibility. It is evidence that a civilization valued the result enough to pay for time with effort, and it helps to remember that precision does not always mean identicality. This is one of the key misunderstandings modern viewers bring to ancient work. We associate precision with standardization, because our world produces precision industrially. Ancient precision could be bespoke. A stone in an Inca wall does not need to match every other stone by factory template. It needs to match the stones touching it. That is a different kind of accuracy, one based on local fit rather than global interchangeability. In some ways, it is more demanding. A machine can produce 1,000 identical bolts. It cannot, without instruction, produce a wall of irregular blocks that lock together beautifully across shifting surfaces. That requires judgment in place, not just replication from a mould, which is why the masonry at places like Sacsayhuaman or Ollantaytambo still leaves such a strong impression. Some of the blocks are large, yes, but beyond size there is the shape logic. Faces meet in ways that distribute load, resist movement, and reduce weak seams. The stones are irregular, yet not random. They appear almost organic in their arrangement, but they are deeply intentional. This is precision without standardization, without digital drafting, without industrial cutting lines. It is precision emerging from repeated contact, test fitting, removal of high spots, and the cumulative experience of masons who knew exactly what a well-set stone should feel like when it finally belonged where it was going to remain. The Roman world offers another important angle because Roman precision often appears not only in cut stone but in spatial control at scale. Roads, aqueducts, arches, vaults, and domes all depend on reliable geometry. An aqueduct is a particularly rude form of truth-telling. Water exposes incompetence efficiently. Too much slope and flow can become destructive. Too little, and the system fails. Maintaining workable gradients over long distances through varied terrain demands surveying competence of a high order. Roman engineers did not have digital terrain models. They had instruments like the groma and chorobates, careful observation, repeated measurement, and administrative structures capable of carrying plans into reality. Their achievements do not rest on one mysterious trick. They rest on process discipline, and process discipline is one of history's most underrated technologies. The Pantheon is perhaps the clearest reminder that ancient precision was not limited to straight lines and right angles. Curves are their own test. A great dome does not tolerate vague intentions. Symmetry, load transfer, material thickness, and formwork all have to cooperate. The oculus does not simply appear because everyone involved feels optimistic. The structure depends on exact relationships between mass and void, between supporting walls and spanning geometry, between material choice and shape. Roman builders managed this without modern structural analysis software, yet not without analysis in the practical sense. They knew where weight had to go. They knew how concrete behaved in large masses. They adjusted materials across the height of the dome. They built with a sensitivity to structure that was empirical, cumulative, and good enough to leave later ages staring upward and pretending to be calm about it. There is a quiet lesson in that. Precision is not always born in theory, and then applied to matter. Sometimes it is born in matter, and then repeated until it becomes reliable knowledge. Ancient builders were often excellent empiricists. They didn't need to derive every principle in formal notation in order to observe what worked, preserve the method and improve it. That is not lesser knowledge. It is differently packaged knowledge. Modern people can be strangely snobbish about this, as if a thing only counts as understanding once it has been translated into the modern language of science. But a mason who consistently produces excellent fit understands something real, whether or not he writes a treatise about it. This becomes especially clear in construction methods that rely on correction rather than prediction. Modern design often aims to model the finished result before fabrication begins. Ancient work, by contrast, could include many cycles of adjustment. A stone is roughed out, brought near its destination, tested, marked, revised, tested again, then finally seated. A surface is pecked, smoothed, checked against a straight edge or template, refined again. A line is laid out with cord, checked by another reference, then confirmed against surrounding geometry. This does not make the process imprecise. In many cases, it makes it robust. Error is not assumed away. Error is expected and managed. There is also a social side to precision that deserves more attention. High accuracy over large projects usually means there were shared standards. Workers had to agree on what counted as straight, square, level, centered, aligned, acceptable. That kind of agreement does not happen automatically in a big labor force. It has to be taught and enforced, which brings us back to training. Ancient precision was sustained not merely by clever devices, but by traditions of workmanship. Somebody taught apprentices how to read a line, how to spot twist in a block, how to keep a vertical true, how to maintain a desired face, how to correct drift before it became visible. A civilization with strong craft lineages could carry this knowledge for generations, and the buildings are often the clearest surviving evidence that such lineages existed. Even decorative work can reveal this discipline. Symmetry in relief carving, repeated motifs laid out across large surfaces, column spacing, pavement patterns, and carved inscriptions all require control. It is one thing to carve a beautiful object slowly in a workshop. It is another to integrate precision across a monumental site with many teams working at once. Standard units of measure become essential here, as do reliable means of transferring proportions from plan to surface. Ancient units were not always universal between cultures, of course, but within a building tradition they could provide the kind of repeatable order that turns vision into construction. And still, the lack of steel, lasers, and computers matters. It mattered then, and it would matter now. Ancient builders paid for precision differently. They paid in time, labour, and procedural repetition. That is why comparisons can be misleading. A modern team might achieve a certain alignment in hours that once took days. Fine, but speed is not the same as superiority in every relevant sense. If the ancient result endures for centuries or millennia and remains accurate enough to provoke modern inspection, then the older method has earned respect even if it was slower. The question is not whether a laser level is useful. It is whether ancient people needed one to produce serious precision. Plainly, they did not. This is also why explanations based on lost advanced machines feel so unsatisfying once you look closely. They assume that precision requires modern-style technology, because they cannot imagine procedural rigor substituting for machinery. But procedural rigor is exactly what complex societies are good at when they care enough. Give a civilization motivation, stable craft traditions, practical mathematics, good reference methods, and a willingness to spend time on correction, and a great many supposedly impossible results become not easy, but entirely human. That said, not every ancient precision problem is fully solved in detail. There are still debates about specific tool marks, specific quarrying sequences, specific methods of lifting or finishing in certain contexts. That is normal. The past is not obliged to preserve full instruction manuals for us. But uncertainty about exact procedure is not the same as evidence of impossibility. In many cases, the broad families of method are clear even when the exact choreography is not. We know enough to understand the achievement, even if we cannot always reconstruct every hour of the workday. And perhaps that is part of why these sites continue to fascinate people who genuinely care about building. They expose a weakness in the modern imagination. We're good at admiring technological power from a distance. We're less good at appreciating quiet control. Ancient precision was often quiet control made durable. A wall that is slightly off will announce it eventually. A foundation that drifts will confess. A misjudged arch will tell the truth in a very direct manner. Structures that remain stable and coherent over long periods are not only monuments to design, they are monuments to repeated decisions made correctly enough. So when people ask how ancient civilizations achieve such accuracy without our tools, the most honest answer is both simple and demanding. They measured carefully, they checked obsessively, they trained skilled workers, they used geometry well, they observed sky, water, and stone. They developed methods suited to their materials. They accepted slowness where slowness improved fit. They corrected errors before those errors spread. And they did all of this inside societies capable of supporting craft at high levels for long periods of time. None of that sounds mystical, which is precisely why it is so powerful. Mystery is easy, discipline is hard. Anyone can wave a hand at a monument and call it impossible. It takes more respect to imagine the actual days behind it. The chords stretched and re-stretched, the surfaces rubbed and checked, the straight edges laid down, the stars observed, the blocks tested and marked, the arguments between workers over whether a line was truly right. The long hours when nothing dramatic happened except that a civilization, through repetition and attention, kept making matter obey form. And once you accept that kind of precision as real, another question immediately steps forward. Because shaping and aligning stone with care is one thing, deciding where the whole structure belongs in relation to the sky is another. And the more we look at ancient monuments, the harder it becomes to ignore how often they seem to know exactly where the sun, moon, and stars are going to be. There is something especially unsettling about an ancient monument that appears to know where the sky is going to be. A wall can impress you with weight, a fitted stone can impress you with craftsmanship, a road can impress you with planning. But when a structure seems to anticipate sunrise on a particular day, or frame the moon at a precise moment, or mirror celestial cycles with enough consistency that modern researchers keep returning with notebooks and instruments, the effect changes. The building stops feeling like a thing placed on the land and starts feeling like a thing placed within a larger pattern. That is often the point where modern people begin speaking in a slightly hushed tone, as if the ancient builders had somehow stepped outside ordinary life and made private arrangements with the heavens. They did not, of course. The sky is available to everyone, which is one of its more democratic features. But what ancient civilizations did have was something no less impressive. They had patience, continuity, and a practical need to pay attention. Long before telescopes, precision clocks, and software simulations, the sky was already one of the most stable reference systems a society could ask for. The sun rose and set. The moon changed shape and position. Certain stars returned seasonally. Solstices and equinoxes altered shadows, daylight, temperature, planting rhythms and ritual calendars. If a civilization watched carefully enough for long enough, it could build that knowledge into architecture, and many did. This is where it becomes important to avoid two opposite mistakes at once. The first is to dismiss astronomical alignment as coincidence, as though ancient peoples simply put buildings wherever the ground seemed convenient, and later generations started seeing patterns in everything. The second is to inflate every apparent alignment into proof of advanced hidden science, as though no one could possibly notice the sun rising in roughly the same place on the same dates year after year, unless someone had secretly invented a doctoral program in astrophysics. Neither view gives ancient builders enough credit. The more reasonable position is also the more demanding one. Ancient societies were often attentive observers of the sky. They integrated that knowledge into monuments for reasons that could be practical, symbolic, political, religious, agricultural, or all of those together. Once you begin from that position, a great many ancient sites become easier to understand and more impressive at the same time, because aligning a monument to the sky is not just a matter of looking upward and pointing somewhere optimistic. It requires repeated observation over time. It requires stable reference points. It requires an understanding of horizon lines, seasonal drift in solar rise and set positions, or the cyclical behavior of the moon. It may require ceremonial calendars or administrative memory that preserves observations across generations. Most of all, it requires the confidence to make architecture answer to events that happen on a larger schedule than individual human convenience. Stonehenge is perhaps the most famous example, and probably the most overburdened by everyone's desire to make it either magical or trivial. Neither is necessary. The monument is already strong enough on its own terms. Its relationship to the solstitial sun has been recognized for a long time, and the broader landscape around it suggests a setting where movement, ritual, burial, and celestial observation may all have mattered. Exactly how every phase of construction connected to astronomy is still debated, as it should be. Debate is not weakness. It is a sign that the evidence deserves careful treatment. But the broad fact remains. The builders placed monumental stones in ways that interacted meaningfully with the sky. That did not happen because someone got lucky with a pile of rocks. It happened because people watched, remembered, and built accordingly. And Stonehenge, useful though it is, can sometimes dominate the conversation so completely that it hides how widespread sky-oriented building really was. In Egypt, for example, solar and stellar relationships were woven deeply into architecture, kingship, and the symbolism of order. Temples were not merely enclosed spaces for rituals. They were often directional statements. Their axes could matter in relation to sunrise, to specific days in the ritual calendar, to the path of light through the building, or to the larger sacred geography linking one place to another. The pyramids too sit within a world where orientation was not casual. Cardinal directions mattered. The sky mattered. The movement of celestial bodies was not background scenery. It was part of the framework through which cosmic stability, divine legitimacy, and royal power were understood. That broader framework is one of the most useful things to keep in mind. Ancient monuments aligned to the sky are not always observatories in the modern sense, and treating them that way can sometimes flatten their meaning. They were often not built for detached scientific study as a modern institution might define it. They were built in cultures where observation, ritual, power, agricultural timing, and cosmology were entangled. A temple may mark solar behaviour not because it functioned like a research instrument for abstract astronomy, but because the sun's behaviour mattered politically and religiously. A city may be planned along a celestial axis, not because urban designers wanted to impress future archaeologists, but because orientation linked earthly order to cosmic order. The sky was not something separate from civilization. It was woven into the terms by which civilization made sense of itself. This is especially clear in Mesoamerica, where architecture, calendrical systems, and celestial observation often meet in very direct ways. At Chichen Itza, the pyramid known as El Castillo is famous for the shadow effect during the equinoxes, when light and shadow combine along the stairway to create the appearance of a serpent descending. There is sometimes debate around how modern tourism and simplified explanation have packaged the event, and that caution is fair. But the broader point remains that Mesoamerican builders and planners were deeply engaged with celestial cycles. This was not decorative interest. It was embedded in timekeeping, ritual, agriculture, rulership, and urban design. A civilization capable of maintaining intricate calendars and large ceremonial centres was perfectly capable of building with the sky in mind. The Maya in particular remain one of the strongest reminders that ancient sky knowledge was neither accidental nor superficial. Their astronomical records, calendrical sophistication, and architectural orientations demonstrate a culture where observation over long periods was central to intellectual life. Structures aligned to solar events, Venus cycles, or other celestial phenomena were not the side hobby of a few priests with excellent neck posture. They were part of a larger system through which time, ritual, political authority, and agricultural life were coordinated. If a building framed a celestial event, that framing was part of an operating worldview, not an isolated technical trick. The same general pattern appears in different forms across the ancient world. In the Andes, for example, certain structures and sacred landscapes appear to have relationships to solstitial light, horizon markers, or ceremonial routes linked to celestial order. Again, the evidence varies by site, and responsible interpretation requires care. Not every window points to a star, and not every doorway deserves its own documentary narrator whispering about lost secrets. But enough cases exist to show that the sky was a design partner in more places than modern people often realise. What changes from culture to culture is not whether the sky mattered, but how it was read and how that reading was translated into built form. This translation from observation into architecture is the real achievement. Watching the sun rise is easy. Turning years of sunrise observation into a reliable building axis is harder. Watching lunar cycles is possible for anyone patient enough. Embedding them into ceremonial space in a way that remains meaningful for a community over generations is a different task entirely. It requires social memory. You need people who know what they are looking for, who pass that knowledge on, and who can convince everyone else that this location, this line, this opening, this stairway or this axis matters enough to build around. That social side of astronomical alignment often gets less attention than it deserves. Modern people like to imagine the solitary genius observer, perhaps standing on a hill with profound cheekbones and a deep knowledge of the stars. Ancient reality was usually more collective. Observation had to be preserved institutionally or ritually. It had to be tied to calendars, festivals, planting times, royal events, or sacred narratives. A solstice only matters architecturally if people care when it occurs. That sounds obvious, but it helps explain why some civilizations built with extraordinary celestial attention, while others expressed their relationship to the sky differently. Architecture reflects values. If the heavens matter to legitimacy, ritual timing, or cosmological order, monuments begin to answer to the heavens. Newgrange in Ireland is an excellent case because it shows how dramatic this relationship can be without requiring enormous urban complexity or later imperial administration. The winter solstice alignment there remains one of the most famous examples in the prehistoric world. At sunrise on the solstice, light enters the passage and illuminates the inner chamber. It is difficult to stand before a fact like that and remain casually dismissive. This is not merely a mound with an accidental crack in the right direction. It is evidence of design tied to the yearly solar cycle. And just as importantly, it is evidence that prehistoric communities, often underestimated by later societies, were capable of long-term observation and architectural response of a very high order. Sites like Newgrange also remind us that celestial alignment often served emotional and symbolic purposes beyond strict practical timekeeping. Winter solstice light entering a chamber is not only useful information about the turning year, it is also an event in darkness, in stone, in ritual space, at a time of seasonal significance. Light becomes part of architecture for a reason. Ancient builders understood this perfectly well. A beam of sunlight moving through a corridor on a particular day is not just a measurement. It is a performance built into the structure. It marks time in a way that the body can witness. The monument becomes not only a static object, but a calendar acted out by light itself. Egyptian temples offer many versions of this principle. In some cases, axial arrangements allow sunlight to penetrate inner areas on significant dates. At Abu Simbel, the alignment of light into the temple interior has long attracted attention, especially in relation to dates associated with the seated statues within. Here again, it is wise to be careful about the details and the tendency for simplified retellings to harden into certainty. Ancient buildings often have long histories, modifications, and interpretive complications. But the essential point is clear enough. Builders in pharaonic Egypt were fully capable of designing structures where the movement of the sun mattered internally, not just externally. The temple could receive light in a patterned way, and that pattern could reinforce sacred or political meaning. Even in the classical Mediterranean world, where architectural discussions are sometimes dominated by proportion, orders, and urbanism, orientation remained important. Greek temples often show meaningful directional choices, whether for ritual approach, local topography, solar behaviour, or relationships to sacred landscapes. Roman planning too, especially in military and urban contexts, could integrate orientation in disciplined ways, though Roman practice also reflects the practical flexibility of an expansionist civilization, happy to adapt to terrain and inherited local traditions. The point is not that every building was a sky machine. The point is that ancient cultures repeatedly demonstrated that they could coordinate architecture with the heavens when they wanted to, and they often wanted to. Why this continues to impress us is not hard to understand. We live in a world where exact celestial information is effortless to obtain, and therefore strangely easy to ignore. Sunrise times, moon phases, seasonal shifts, planetary positions, all of it sits quietly in phone applications waiting to be consulted and rarely thanked. Ancient builders had no such convenience. They had to earn their sky knowledge through watching, not once, but many times. They had to note where the sun rose against the horizon at different parts of the year. They had to remember where the moon behaved unusually. They had to preserve this knowledge across seasons and perhaps across generations. That kind of patient observation is difficult for modern people to imagine because we tend to outsource it. Ancient societies often could not. And because they could not, they became better observers than we usually give them credit for. Agricultural life helped. Ritual cycles helped. Navigation in some cultures helped. But beyond utility, there was also the fact that the sky itself was one of the few regular systems available on a truly large scale. For societies trying to anchor time, authority, and sacred order, the heavens offered a model of recurrence that architecture could borrow. A monument aligned to the solstice does not merely point to the sun. It says that the builders understand when that event occurs and care enough to make stone acknowledge it. Of course, there are limits to interpretation. Archaeologists are quite right to insist on rigour. Not every perceived alignment is intentional. With enough ancient sites and enough enthusiastic observers, chance patterns will appear. Horizon changes over time. Buildings are modified. Context is lost. Some monuments may have multiple phases or functions, making any single astronomical reading incomplete. There is also the risk of selective attention, where people remember the alignments that work and quietly forget the ones that do not. This is why serious archaeoastronomy requires more than fascination. It requires measurement, context, caution, and a willingness to say maybe instead of certainly when the evidence is not strong enough. That caution does not weaken the field. It protects it. Ancient builders deserve evidence-based admiration, not decorative speculation. The best examples are compelling precisely because they survive careful scrutiny. When a monument repeatedly demonstrates a meaningful relationship to celestial events within a cultural framework that values those events, the result is powerful. It shows that architecture was doing more than occupying land. It was participating in time. That phrase matters because time is really at the centre of this subject. Monuments aligned to the sky are often monuments aligned to recurring time. They catch the year at a particular point. They stage light on a specific morning. They organise ritual around predictable cosmic motion. In that sense, these buildings are cousins to calendars, but much heavier and considerably less convenient to hang on a wall. Still, their purpose may overlap. They make recurrence visible. They turn the abstract passage of seasons into something embodied and public. You can walk into it, stand inside it, gather around it, and know that the same event was meant to happen there again next year. This ability to bind time into architecture gives ancient monuments a kind of durability modern schedules do not have. A paper calendar can be lost. A digital calendar can send an alert you immediately ignore. A temple or mound or ceremonial platform aligned to the sun makes a stronger impression. It tells a society that the sky has returned to an appointed relationship with the built world. That is more than convenience. It is order enacted. It may help explain why these structures often feel so serious. They are not just places, they are mechanisms for putting human life into contact with larger cycles. And this, perhaps, is why the subject still has a hold on modern imagination. People sense that sky-aligned monuments represent a form of attention we have partly lost. Not scientific knowledge in the modern institutional sense, because we know far more now in absolute terms, but attentional knowledge, the kind that comes from repeated direct observation, from caring about horizon lines, from noticing light in stone spaces, from remembering what happened last year and the year before and the year before that. Ancient civilizations often had this attention because their worlds encouraged it. When the sky regulates agriculture, ritual, legitimacy and memory, you watch. And if you watch long enough, eventually you build. So when we say ancient monuments were aligned to the sky, what we really mean is that ancient builders were working at the intersection of observation, meaning, and architecture. They were not only raising stones and walls, they were fixing events into place. They were making structures that could catch a sunrise, mark a season, honour a cycle, or frame a pattern larger than any one human life. That does not require modern instruments. It requires serious cultures of watching, remembering and building with intention. And once that becomes clear, another question begins to push forward. Because it is one thing to notice that ancient builders aligned monuments to celestial events. It is another to ask how much practical knowledge sat behind all of this without ever becoming a formal written science in the way modern people expect. Monuments do not rise from reverence alone. Observation has to pass into technique somewhere, into methods, instructions, habits and craft traditions that people knew how to use even if they did not leave behind a handbook explaining every step. Which is where the conversation turns from what they aligned to how much of their engineering language has disappeared with them. Once you begin looking closely at ancient monuments, a strange problem appears. The structures are still here, or enough of them are. The walls remain, the foundations remain, the cut faces of stone remain, the channels, vaults, terraces, stairways, platforms, retaining systems and drainage routes remain. What often does not remain is the full working vocabulary that produced them. We inherit the outcome, but not always the language of process. We see the sentence, but not the grammar. And that is one reason ancient engineering can feel more mysterious than it really was. It is not only that some techniques have been lost, it is that the mental world in which those techniques made ordinary sense has often gone missing with them. Modern people are used to engineering being documented in a certain way. We expect drawings, specifications, calculations, technical manuals, standard units, explicit models, supply lists, failure analyses and revision histories, ideally all stamped, archived, searchable, and irritatingly labelled in a folder someone else forgot to update. When these things exist, we feel comfortable. We can trace decisions, we can reconstruct intent, we can see not just what was built, but how people thought about building it. Ancient civilizations did not always leave us that kind of paper trail, and when they did, it was often incomplete, fragmentary, specialized or destroyed by the sort of events that also tend to end civilizations more broadly. That gap matters because skill is not only in the hands, it is also in the words people use to guide those hands. Every trade develops a language for tolerances, surfaces, faults, methods, tools, sequences, materials and judgments that outsiders barely notice. A master mason and an apprentice do not need a philosophical essay to communicate what a block is doing wrong. They need terms that are short, specific, practical and tied to action. The same goes for quarry crews, surveyors, carpenters, plasterers, metal workers, hydraulic engineers, and road builders. A civilization that builds at a high level accumulates not just techniques, but speech habits around those techniques. Some of that language may enter records, much of it may never be written down at all. This is one of the most important things to keep in mind when thinking about the ancient world. Lost knowledge is not always a matter of secret formulas sealed in a vanished library. Sometimes it is much less dramatic and far more consequential. Sometimes it is the disappearance of workshop routines, rule of thumb measurements, remembered sequences, local material judgments, and entire chains of apprenticeship. A method does not vanish because someone burns the final copy of a book titled How We Built the Temple. It vanishes because the people who knew how to read stone, mix binders, choose timber, prepare foundations, lay out curves, check gradients, and train the next generation stop doing those things in a continuous way. That loss can happen surprisingly quickly. A political collapse interrupts patronage. A conquest breaks labour systems. Trade routes shift. Quarry access becomes unsafe. Religious change makes certain building types less important. Skilled workers move, die, or are absorbed into different economies. Raw materials become harder to obtain. Administrative institutions weaken. Within a few generations, a craft tradition that once felt ordinary can become exceptional, then rare, then misunderstood. Centuries later, a surviving structure sits before us looking almost tauntingly competent, while the language that once explained each step has dissolved into fragments. Roman concrete is one of the clearest examples, though it is often described in a way that makes it sound more magical than it needs to be. The Romans did not stumble into a miracle paste under suspiciously cinematic lightning conditions. They worked within material traditions that included lime, volcanic ash, aggregate selection, water, and practical construction methods refined over time. In some marine contexts especially, Roman concrete has proven remarkably durable, and modern materials scientists have spent considerable effort studying why. The point here is not that the Romans had access to supernatural chemistry. It is that they had a working material language embedded in practice, supply, and engineering culture, which allowed them to use available ingredients in ways suited to long-term performance. Later societies did not simply inherit the exact same system in full. The structures survived, the full procedural world around them did not, and that is where the phrase lost language becomes useful. Ancient engineering was not just a list of techniques, it was a framework for seeing problems. A Roman builder approaching a harbour, a vault, or a bath complex was not inventing everything from nothing each time. He was drawing on inherited categories. He knew which materials belonged in which conditions, what formwork implied, how loads behaved in arches, what certain soils meant for foundations, how moisture affected construction sequences, how labour should be staged, and what previous works had already demonstrated. Some of that understanding could be written. Some of it lived in experience. Some of it may have been so ordinary that nobody thought to explain it in detail because everyone in the profession already knew. That last part is especially inconvenient for historians. The most important knowledge in a functioning system is often the least likely to be elaborated in surviving texts. If every trained builder already understands how to prepare a bedding surface or judge whether a stone is safe to detach, the written record may focus on commissions, payments, dimensions, dedications, or high-level principles, rather than the practical details modern researchers desperately want. It is a little like trying to reconstruct an entire modern construction culture from a ceremonial opening plaque, a few invoices, and a broken set of tools. You would learn something certainly, but probably not enough to explain why the roof still does not leak. The same challenge appears in stonework traditions across the Andes. Inca masonry is often admired for its fit, stability, and seismic resilience, and rightly so. But the people who built those walls did not leave behind a convenient handbook explaining every stage in language tailored to future viewers with internet access and a mild tendency toward speculation. What survives instead are walls, quarry traces, transport evidence, tool marks, unfinished works, chroniclers' descriptions of varying quality, and the broader pattern of a civilization that clearly possessed very strong practical knowledge of stone and terrain. Enough survives to show that the work was disciplined and repeatable. What does not survive in full is the living workshop speech through which experts would once have taught, corrected, and refined that work. There is a tendency to imagine this kind of lost knowledge as if it were exotic by definition. In reality, most of it was probably practical to the point of boredom. Which wedge where? How wet the path? What sound a good block makes when struck? How much daylight should show under a straight edge before a face is corrected? Which stones belong low? Which belong high? How much settling to expect? When to stop cutting because the grain is turning against you? Which foundation soils need extra preparation? How to sequence labour so the masons are not waiting on transport crews, or the crews are not delivering blocks before the bedding surface is ready. None of this sounds glamorous, and that is exactly why it matters. Civilizations do not build well by surviving on mystery. They build well by normalizing competence. In fact, one of the great mistakes people make when discussing ancient engineering is assuming that what we do not know must have been hidden in the dramatic parts. Usually the opposite is true. The grand design idea might be relatively visible. The hard part is reconstructing the chain of ordinary decisions that turn the idea into matter. That is where the lost language lives. In the repeated verbs of construction, in the terms workers used among themselves, in the gestures that accompanied those terms, in the way a foreman could point to a block and make an adjustment without delivering a lecture on the philosophy of alignment. Egypt offers another version of this problem. The monuments survive in enough abundance to create a dangerous illusion that we understand the whole system. We understand a great deal, certainly. Quarrying, transport, labour organisation, surveying, stone dressing, and monumental planning in ancient Egypt have all been studied extensively, and many past claims of impossibility have been reduced by patient archaeology into demanding but plausible sequences. Yet even there, much of the living technical culture is irretrievable in full. The builders' villages, graffiti, work gangs, unfinished monuments and tool traces all tell us important things. They show coordination, specialisation, labour identities and procedural stages. But they do not fully return to us the continuous voice of the workshop. We can infer the method. We cannot always hear the conversation. And hearing the conversation would change everything. It would make the monuments feel less like static puzzles and more like active job sites. You would know which imperfections mattered and which did not. You would know when a crack meant abandon the stone and when it meant adjust the plan. You would know which dimensions were sacred, which were approximate, which were politically non-negotiable, and which could be corrected later with facing or plaster. You would know what was considered elegant, what was considered acceptable, what counted as a risk, and what sort of errors made older craftsmen sigh in disappointment at younger ones. In other words, you would not only know the engineering, you would know the culture of engineering. That culture is often harder to recover than the engineering itself because ancient knowledge was not always divided the way modern disciplines divide it. We separate architecture, engineering, religion, administration, astronomy, and material science into distinct fields. Ancient civilizations often did not. A temple axis could be a technical matter, a sacred matter, and a political matter at the same time. A terrace system could be agriculture, hydrology, and state organization all at once. A city wall could be defense, labor mobilization, social identity, and stone logistics in one package. This means that the lost language of ancient engineering may also be entangled with lost language of ritual, governance, and cosmology. The builder's world was not always divided into neat professional boxes. This complicates interpretation but also makes it more interesting. A decision that looks purely symbolic may also carry structural logic. A choice that appears purely technical may also reinforce political authority. Monumental works do not emerge from equations alone. They emerge from what a civilization thinks is worth building, worth aligning, worth maintaining, worth paying for, and worth teaching. Once those priorities change, technical traditions can shift with them. A society that no longer builds giant stone tombs may not bother preserving the full logistical knowledge required to make them. A society that turns away from volcanic concrete toward other materials may lose some of the finer points of the earlier mixed design, not because the knowledge was false, but because it was no longer central, And then there are the written sources we do have, which must be handled with the sort of patience that ancient builders themselves would probably recommend. Technical writing from antiquity exists in some traditions, but it is often partial. Roman authors, for instance, can be extremely valuable, yet they do not always write with the step-by-step clarity a modern engineer might hope for. They assume context. They omit what seems obvious to them. They mix observation, prescription, inherited wisdom, and social values. They're also not always describing the full range of a local variation across an empire. The same is true elsewhere. Texts survive unevenly. Some are practical, some are ceremonial, some are copied badly, some are translated through centuries of misunderstanding, some are simply gone. This leaves modern researchers doing something both difficult and admirable. They reconstruct ancient engineering languages from evidence spread across objects, sites, experiments, and fragments of text. They look at tool marks, quarry faces, failed cuts, unfinished surfaces, mortar composition, foundation settlement, block placement patterns, erosion behaviour, transport routes, and surviving administrative records. They attempt replications. They calculate labour inputs. They compare one site to another. They try to determine not just whether something could have been done, but whether it could have been done repeatedly and within the broader social systems known to exist. It is patient work and rarely produces the kind of dramatic certainty popular audiences imagine history owes them. But that uncertainty is not weakness. It is honesty. Ancient engineering languages are not fully recoverable because they were living things, not frozen formulas. They existed in bodies as much as in records. A mason's hand placement, a quarry worker's listening, a surveyor's eye at dawn, a labour organiser's sense of timing, a plasterer's judgment by feel, a carpenter's understanding of temporary support. These are all forms of knowledge that can be partly inferred and partly demonstrated, but never perfectly restored once the tradition breaks. Even modern crafts lose things this way. A workshop closes, a specialist retires, a material falls out of use. A younger generation moves to different work. 20 years later, someone says, "Why don't they make them like that anymore?" Usually because the making was never just a recipe, it was a culture. There is another reason the lost language matters, and it is not only academic. It changes how we judge ancient people. Without their technical speech, we are tempted to project our own categories onto them. We imagine what they must have known, or could not have known, based on what feels intuitive from a modern viewpoint. This is risky. Ancient builders may have lacked our theoretical language in some domains, while possessing stronger practical language in others. They may not have described stress paths the way a modern engineering text would, yet they may have had very clear rules for where mass belongs and where openings become dangerous. They may not have had a formal material science of binders, yet they knew which mixtures endure in wet conditions. They may not have used our vocabulary for seismic response, yet their masonry systems behaved accordingly. This is why underestimating ancient engineering often begins as a language problem. We look for familiar forms of explanation, and, finding them incomplete, mistake absence of familiar wording for absence of knowledge. But knowledge does not stop existing because it is stored differently. If anything, the surviving monuments prove that the knowledge was real enough to matter. A wall that survives earthquakes is an argument. A concrete harbour that resists the sea is an argument. A precisely graded water system is an argument. The structure itself becomes the surviving sentence of a language whose full grammar has faded. And perhaps that is why ancient engineering continues to attract so much speculation. People sense the gap between result and explanation, and nature dislikes a vacuum almost as much as human imagination does. Where procedural detail is missing, fantasy enters. Hidden civilizations, impossible tools, forbidden sciences, and all the rest gather around monuments whose real crime is simply that they are better than the average lazy summary of the past. Yet if we pay attention, the gap does not actually point toward magic. It points toward lost continuity, toward broken chains of training, toward technical cultures that once made sense of stone, water, light and load, in ways their descendants no longer practiced regularly enough to remember. That is a humbling realization, and a useful one. It means the ancient world does not merely challenge us with isolated feats. It challenges us with the possibility that knowledge is more fragile than we like to think. Civilizations can know how to do extraordinary things and still fail to pass the full method forward. Not because humans become less intelligent, but because institutions change, priorities change, patronage changes, and the language of doing disappears faster than the stone it once arranged. So when we stand before ancient monuments and feel that slight frustration of not quite knowing how every step was carried out, what we are really feeling is the edge of a vanished technical conversation. The builders knew what they were doing well enough to make the result endure. We know enough to admire it, study it, and in some cases partly replicate it. What lies between those two states is the missing middle, the everyday language of craft, instruction, correction, and shared standards that once turned ambitious designs into reliable reality. And once you start noticing how much of that language has fallen silent, it becomes easier to appreciate why some of the old materials themselves still seem to speak more clearly than the people who made them, especially when those materials have survived so well that modern builders are still trying to figure out exactly what, in practical terms, gave them their extraordinary staying power. If materials sometimes outlast the language that once explained them, then entire carved cities take that feeling and make it much harder to ignore. A single wall can leave questions, a platform can leave questions, a giant stone can leave questions. But when a civilization does not merely build on the land and instead begins shaping the land itself into a place of movement, storage, ritual, defense, water management, and daily life, the scale of intention changes. You're no longer looking at a monument that happens to stand in a landscape. You're looking at a landscape that has been taught to behave like architecture. That is one of the reasons rock-cut and terrain-shaped cities remain so striking even after the first shock of their appearance has settled. At first glance, they can seem almost easier than freestanding construction. A casual modern observer might think, well, the mountain was already there, the cliff was already there, the desert face was already there, so perhaps carving into it was merely a matter of removing the bits that were in the way. That idea has the advantage of sounding practical, and the disadvantage of being profoundly wrong. Building into rock solves some problems, certainly. The walls do not need to be assembled from separate blocks if the wall is the mountain itself. But it creates a whole new family of difficulties. You have to understand the rock body you're entering. You have to know where it is sound and where it is weak. You have to manage interior space by subtraction rather than addition. You have to deal with ventilation, drainage, access, structural stability, and the deeply inconvenient fact that once you carve too much out of the wrong place, putting it back is not a popular option. This is why cities carved from rock, desert, and mountain are so useful to this story. They reveal ancient engineering in a form that cannot be reduced to simple lifting or stacking. They show what happens when builders treat terrain not as background but as raw material. And once they do, the result can feel less like construction in the ordinary sense, and more like negotiation with geology. The city is still man-made, but it has not been placed beside the earth so much as argued out of it. Petra is probably the most famous example, and with good reason. It is one of those places that risks sounding overpraised until you actually look at what the Nabateans were doing there. The first images most people know are the great facades cut into rose-coloured sandstone, especially Al-Khazneh, the structure often called the Treasury, which emerges at the end of a narrow gorge with such theatrical control that even modern tourism has not fully managed to ruin the effect. But the facades, dramatic as they are, can distract from the broader intelligence of the site. Petra was not simply a collection of decorative fronts carved into cliff faces by people with excellent patience and a fondness for columns. It was an urban system in an arid environment, shaped by a civilization that understood trade, water, terrain, and defensive geography exceptionally well. That last part matters. Petra sits in a landscape that could easily look harsh to anyone not trained to read it properly. Rock, heat, seasonal water, narrow passages, exposed surfaces, difficult routes. The Nabateans did not merely tolerate that environment, they made it productive. Water management in Petra was not an optional convenience. It was the difference between a ceremonial site, a temporary stopping point, and a functioning city tied into long-distance trade networks. Channels, cisterns, dams, reservoirs, and carefully directed flow allowed water to be captured, stored, controlled, and protected from destructive flash flooding. That achievement deserves almost as much admiration as the stone carving itself, perhaps more, because rock-cut beauty without hydraulic competence would have remained little more than an expensive way to die of thirst. This is one of the recurring truths in ancient engineered landscapes. The visible spectacle often depends on an invisible system. A facade catches the eye. A water channel keeps the city alive. A carved tomb impresses visitors. A controlled runoff system prevents erosion and collapse. When modern people encounter Petra and focus only on the monumentality of the stone fronts, they are seeing only part of the intelligence involved. The city worked because the Nabateans understood that terrain is never just scenery. It is route, barrier, resource, threat, and opportunity all at once. Their city carved from desert stone was also a city of flow, storage, and timing. And Petra is far from the only site where this deeper intelligence reveals itself. In Cappadocia, and especially in the underground cities such as Derinkuyu, the problem takes a different form. Here the astonishment does not come first from facades or visible grandeur. It comes from the realization that entire multi-level spaces were created below ground in soft volcanic rock, with ventilation shafts, storage areas, living quarters, defensive closures, and internal circulation arranged in ways that still make modern visitors slow down and ask whether they have understood the scale correctly. Derinkuyu and related underground complexes are not simply caves people happen to use. They are organised, excavated environments. People made decisions down there. Decisions about air, access, security, food, animals, water, and survival, under conditions where getting any of those wrong becomes memorable for all the wrong reasons. Soft tough is in one sense a gift. It can be carved more readily than harder stone. In another sense, it is a trap. Material that is easy to excavate also requires careful judgment about shape, support, and long-term use. Underground space is unforgiving in its own special style. A poorly ventilated room becomes miserable, then dangerous. A badly designed passage turns circulation into chaos. A weak section becomes a structural risk. The remarkable thing about places like Derinkuyu is not that people went underground. Human beings will go underground for many reasons and are seldom shy about the attempt. The remarkable thing is how systematically these underground environments were organised. Vertical connections, communal spaces, protective stone doors, ventilation systems, and spatial layering all point toward communities that understood subterranean life as a managed engineering problem, rather than a desperate improvisation. There is something instructive in that contrast with Petra. Petra externalizes itself in monumental carved faces and controlled desert hydraulics. Derinkuyu internalizes itself in hidden volume and careful environmental management. One works with cliffs and wadis, the other with subterranean chambers and shafts. One announces itself, the other conceals itself. Yet both show the same underlying principle. Ancient builders were not only capable of constructing individual structures, they could reshape whole spatial worlds out of existing geological conditions. They could read a place deeply enough to know not just where to build, but how the ground itself might become the building. This same principle appears again in South Asia, though in forms so varied they almost seem to belong to different categories until one looks more closely. The rock-cut cave complexes of Ajanta and Ellora in India offer another version of city-like carved space, one in which religious architecture, artistic labour, circulation, and geological excavation come together with extraordinary confidence. These are not casual caves with decorative additions. They are engineered interiors made through subtraction, with columns, halls, shrines, facades, and sculptural programs extracted from living rock. That phrase matters, extracted from living rock. Not assembled piece by piece in the ordinary way, but released by removing what did not belong. It is difficult to overstate how demanding that process is. A freestanding building allows a certain sequence of correction. If a column is made badly, another can sometimes replace it. If dimensions drift, compensation can occur in later components. In rock-cut architecture, the order of error changes. You are carving inward. The material is continuous. The design has to be carried in the minds, marks, and routines of the builders with unusual discipline. Proportions must be anticipated. Voids must be planned. Pillars left in place must have enough mass and proper position. Ceiling surfaces, wall depths, sculptural programs, and internal alignment all have to emerge coherently from removal rather than assembly. One cuts toward architecture rather than constructing it outward. That changes the logic of everything. Ajanta and Ellora also show that ancient builders could work at the intersection of technical competence and aesthetic ambition without treating them as separate worlds. The structural act of excavation and the visual act of sacred design were joined. A hall had to stand. It also had to mean something. The result is a reminder that ancient engineering was rarely just utility stripped of culture. It was often the opposite. The engineering became more demanding because the cultural program was so ambitious. A society did not simply want shelter or enclosed volume. It wanted sacred procession, durable symbolism, carved narratives, ordered space, acoustics, light, and permanence. Every added expectation made the technical challenge harder. Sigiriya in Sri Lanka presents yet another variation, where a dramatic rock outcrop was transformed into a heavily engineered royal and ceremonial landscape. Here the accomplishment is not only carving into rock, but organising access, fortification, water gardens, terraces, and elevated construction around a geological feature that already dominates its surroundings. The site demonstrates something ancient builders repeatedly understood better than we often assume. Spectacular natural topography is not enough on its own. To turn a rock mass into a functioning power centre requires root control, hydraulic planning, surface modification, and deliberate visual strategy. A steep natural formation may look defensible and impressive, but until paths, platforms, retaining works, and water systems are integrated, it remains only potential. This is true in mountain environments more broadly. Ancient terrace systems, fortifications, and hilltop settlements across the world show that building into slopes is as much about management as placement. Mountain construction is not just a matter of putting stones on an incline and hoping gravity remains in a generous mood. It requires retaining walls, drainage, slope stabilization, path networks, staged surfaces, and a practical understanding of how rain and soil will behave over time. In the Andes, for example, urban and agricultural landscapes alike reveal a civilization deeply attuned to gradient, runoff, and the conversion of difficult terrain into productive and stable human space. Machu Picchu is often admired for its setting, and it should be, but the setting can mislead people into thinking the site is chiefly a triumph of placement. It is also a triumph of preparation. Terraces, drainage, foundations, and stonework allowed that dramatic ridgetop environment to function without simply dissolving downslope in bad weather. That last point is one of the least glamorous and most important in all terrain-based ancient engineering. Water is the strictest critic. Build badly on a slope, and rain will eventually publish your mistakes. Build badly in desert canyons, and flash floods will educate you. Build badly underground, and moisture or airflow will create a different sort of correction. Cities carved from rock, desert, and mountain impress not only because they exist, but because many were made to endure environmental conditions that punish carelessness. Surviving carved landscapes are almost always evidence of systems hidden beneath visual drama. Drainage cut into stone, channels hidden beside paths, retaining logic embedded in terraces, storage integrated into topography, and access routes that did not happen to work by accident. There is also the question of labour organisation, which carved cities expose in a particularly revealing way. A freestanding structure can sometimes be imagined in modular steps. Quarry here, transport there, lift, set, finish. A carved environment often demands different sequencing. Workers must remove vast quantities of material in planned order. Debris has to go somewhere. Access to the workface has to remain possible. Layout must be preserved as more material disappears. In underground or cliff-cut settings, light itself becomes a work problem. Ventilation becomes a work problem. Safety becomes a work problem, even if ancient states and patrons were not always known for making safety their most tender priority. The point is not that the labour was pleasant. The point is that it had to be organised. An organisation on this scale suggests something again that ancient sites keep repeating to us. These were not people improvising heroically in a vacuum. They were societies with enough continuity and command to sustain highly specialised terrain transformation. Whether for trade, defence, religion, rulership, refuge or prestige, they could direct substantial effort toward making difficult landscapes inhabitable on their own terms. That often required knowledge of local geology so practical it almost disappears from the record because it was never written in the way modern readers expect. Builders knew which rock could be carved cleanly and which would betray them. They knew where water collected and how to intercept it. They knew how much space could be removed while leaving enough behind. They knew where a path should turn, where a wall should retain, where a stair should rise, where a channel should cut, and where not to trust the mountain. This is one reason carved and terrain-shaped cities can still feel beyond easy reproduction. Of course, modern engineering can excavate, tunnel, terrace, and anchor. It can do so with remarkable power, but exact replication of many ancient carved urban forms would still be difficult, expensive, and in some cases culturally irrational by our standards. We do not usually carve monumental sacred facades into cliff systems because reinforced concrete and steel are available, and accountants remain energetic in their objections. We do not normally hollow large refuge cities into soft rock because surface infrastructure is easier to regulate and connect to modern services. We do not terrace mountainsides at ancient scales with the same labour logic because our economies value time and labour differently. Yet the fact that we would choose different methods does not reduce the sophistication of the old ones. If anything, it reminds us that ancient builders solved problems directly from terrain, with a confidence modern systems often prefer to avoid through substitution. There is another lesson here as well, one that becomes clearer the more these sites are compared. Ancient urbanism was not always about imposing geometric order onto a blank plane. Sometimes it was about entering into the irregularity of a place and making that irregularity legible, usable and meaningful. Petra follows canyon and cliff. Derinku descends into workable rock. Ajanta and Ellora occupy escarpments. Sigiriya commands a rock mass and the landscape below. Machu Picchu occupies a ridge between peaks and organises its surfaces with careful adaptation. In each case, the city or complex is not merely located in a dramatic setting. It has been intellectually and physically fitted to that setting. That requires a different kind of design imagination from the one that prefers flat ground and neat grids. It also requires confidence in long-term maintenance. Carved cities do not simply finish themselves once excavation is done. Water channels need clearing, access routes need repair, surfaces weather, retaining systems settle, underground spaces need management. Erosion is patient, plant growth is opportunistic. If a civilization builds deeply into terrain, it is committing itself to an ongoing relationship with that terrain. This is another reason so many such sites are bound up with strong political or sacred institutions. Ordinary household decision-making does not usually sustain mountain-scale maintenance indefinitely. States, temple systems, elite centres, and trade hubs are better at insisting that a place remain functional even when the work is tedious. All of which brings us back to the central discomfort these places create in the modern imagination. They are too large and too integrated to dismiss as simple carving, yet too grounded in actual geology and labour to justify fantasy. They force a more serious response. A city in rock is not just an artistic gesture. It is geology turned into root, wall, chamber, storage, ritual, drainage, and defence. A city in desert stone is not just a set of facades. It is hydrology, transport, topographic strategy, and social planning. A city in mountain terrain is not just scenic architecture. It is slope control, agricultural engineering, path logic, and environmental adaptation. Ancient civilizations were able to think in these terms because they were often working closer to the raw behaviour of land than most modern urban systems like to admit. And perhaps that is why the best of these sites still feel so direct. They have not been separated from the earth by thick layers of abstraction. They are made from the earth, into the earth, against the earth, with a realism about material and terrain that is hard to miss once you notice it. These were builders who did not only know how to erect structures, they knew how to occupy difficult landscapes without pretending those landscapes would become easier simply because a ruler wanted a monument there. So when we speak of cities carved from rock, desert and mountain, we are really speaking about civilizations that treated terrain as a partner in engineering, sometimes a stubborn partner, sometimes a generous one, but never a passive backdrop. They read cliffs, slopes, canyons and ridges as opportunities for architecture, storage, defence and ceremony. They understood that the earth itself could become part of the city if one knew where to cut, where to leave mass, where to route water, and where to stop before the whole arrangement began arguing back. And once that becomes clear, the next question almost asks itself, because shaping a city from geology is one thing, but making materials within those environments last for centuries or millennia is another. Some ancient civilizations didn't only master the places they built in, they also produced substances within those places that continue to raise an awkward question for the modern world about whether all improvement really moves in only one direction. Because shaping a city out of mountain or desert stone is only half the achievement. The other half is the material itself, not just where it came from, but what people knew how to do with it once they had it. This is where the modern imagination often takes another wrong turn. We are very good at assuming that ancient materials must have been crude simply because they were ancient. We hear the words lime, ash, copper, iron, charcoal, sand, clay, and our minds quietly place them in the category of early attempts, charming but limited, like a first draft of civilization waiting patiently for modern chemistry to arrive and rescue it. Then we look at what some of those materials actually did, how long they lasted, how well they handled water, salt, stress, heat, weather, and time, and that tidy little story begins to wobble. Because some ancient civilizations were not merely using available materials, they were refining them with a level of practical sophistication that still causes trouble for modern confidence. Not trouble in the sense that we cannot make advanced materials now. Clearly we can. We make alloys, polymers, composites, and engineered concretes that ancient people would have regarded with a sensible mixture of admiration and deep suspicion. But that is not the question. The question is narrower and more uncomfortable. Can we always reproduce what they achieved in the exact way they achieved it, with the same long-term performance, the same local material intelligence, the same durability under specific conditions, and the same economy of ingredients? Often, not as easily as we would like. Roman concrete is the most famous example because it has spent a very long time behaving like an extremely impolite reminder that durability and modernity are not synonyms. If you walk through the remains of Roman harbours piers, seawalls, vaults, baths, cisterns, domes and foundations. You're looking at a civilization that understood binders far better than the phrase ancient concrete tends to suggest. The Romans did not simply throw gravel into lime and hope the empire would hold together out of civic optimism. They developed and deployed concrete as a serious structural material, and in marine environments in particular, some Roman concrete has shown extraordinary endurance. This is one of those facts that sounds quaint until you remember how hard marine construction is on modern materials. Salt water is not a forgiving companion. Waves pound, chloride penetrates, cracks widen, metal reinforcement corrodes, and the sea, with its usual lack of concern for human schedules, just keeps turning up every day to continue the argument. Modern concrete is very capable, but it often depends on still reinforcement for certain forms of strength, and in marine environments that reinforcement becomes one of the vulnerabilities. Roman marine concrete worked differently. It used lime and volcanic ash, especially pozzolanic materials, creating reactions that allowed the concrete to set underwater and, over time, in some cases, become remarkably resilient. Studies of surviving Roman marine structures have suggested that their long-term performance may involve mineral growth within the concrete matrix, strengthening it in ways that modern builders did not routinely reproduce because modern construction followed different priorities. That last part is worth pausing over. The Romans were not working with some magical recipe whispered to them by Neptune after a favourable tide. They were working with locally available volcanic materials, lime production, aggregate, practical experience, and repeated use in real structures. They learned, through application, which combinations performed well and where. They had materials suited to their building culture and their environment. Modern concrete, by contrast, evolved in industrial contexts with different goals: speed, standardization, compressive performance, compatibility with steel reinforcement, cost efficiency, and large-scale modern infrastructure demands. In other words, we did not fail to inherit Roman marine concrete because we were too foolish to notice that durable materials are useful. We moved into a different material regime with different assumptions. Only later did we start looking back and realizing that some of the old choices were better than expected in specific settings. That is often how ancient material knowledge works. It is not universally superior. It is locally excellent. Roman marine concrete is not the answer to every engineering problem from sidewalks to spacecraft. But in its own domain, it continues to demand respect. It shows that a civilization with enough practical experimentation, enough continuity, and enough willingness to build at scale can arrive at a material solution that later societies do not automatically surpass in every dimension. Progress, as ever, turns out to be less like a staircase and more like a very complicated storage room where some useful things are constantly being misplaced. And concrete is only the beginning. Metals make the picture even more interesting, partly because metal has such a strong hold on modern imagination. We tend to treat metallurgy as one of the great markers of technological seriousness, and to be fair, it is. Extracting metal, refining it, alloying it, shaping it, heat-treating it, and understanding how it behaves under use are all difficult and consequential achievements. What is easy to forget is that ancient metallurgists were often working with extraordinary subtlety. They did not possess modern spectroscopy or industrial furnaces with digital controls, but they did possess repeated observation, furnace management, fuel knowledge, or selection, and a practical sensitivity to heat, carbon, slag, impurities, and cooling behaviour that could produce results still admired now. Take wood steel, for instance, the high-carbon crucible steel associated especially with South Asia and famous in connection with the blades later known in some traditions as Damascus steel. Here again, the internet has made a hobby of turning a real achievement into decorative mythology. No, these blades were not lightsabers. They did not slice through cannons, dishonesty, and the laws of physics all at once. But yes, they were remarkable. The microstructures achievable in carefully produced crucible steels, the combination of hardness and toughness under the right conditions, and the distinctive surface patterns associated with skilled forging and heat treatment made them genuinely special. What matters for our purposes is not just that such steels existed, but that the full conditions for reproducing some traditional forms of them were historically complex enough that later makers struggled to recover them reliably once the original production chains broke. That struggle tells us something important. Material excellence often depends on more than a recipe. It depends on ore sources, impurity profiles, crucible design, furnace temperatures, fuel type, working sequence, forging temperature, thermal cycling, and the judgment of craftspeople who know exactly when a process is behaving properly. Change the ore chemistry and the steel changes. Change the heat and the steel changes. Change the timing, the cooling, the reduction environment, the working pattern, and the result changes again. This is why recovering a lost metal is so difficult. You're not trying to bake the same cake in a slightly different kitchen. You're trying to reconstruct an entire materials ecosystem from fragments. While the original minds may be exhausted, the original workshop language is gone, and the original masters are unhelpfully dead. And yet people did this work repeatedly across the ancient world. Bronze Age societies understood alloying well enough to transform copper into a dramatically more useful material through the addition of tin or other elements. Ancient smiths learned how to produce edge tools, weapons, fittings, vessels, mirrors, and decorative objects with properties suited to their purposes. Ironworking expanded that difficulty even further. Smelting iron is not straightforward. Bloomery processes produce material that must then be worked, consolidated, adjusted, and repeatedly refined. This is not a realm of simple discovery followed by permanent mastery. It is a realm of heat management, slag control, oxygen control, fuel control, and relentless practical judgment. Even something as seemingly simple as a reliable bronze or iron object reflects a chain of difficult successes. Ore must be available and recognized as worthwhile. Fuel, especially charcoal, must be produced in quantity. Furnaces must reach sufficient temperatures and maintain them. Airflow must be controlled. Impurities must be managed. Working temperatures must be judged by eye, by colour, by experience. A metalworker without thermometers can still know a great deal about heat. In fact, many traditional crafts reveal an uncomfortable truth for modern people, which is that formal measurement is not the only path to repeatable control. Hands, eyes, ears, and inherited procedure can take a society surprisingly far. This does not mean ancient materials were universally better. It means they were often more tailored to long-term human familiarity with a specific environment than we casually acknowledge. Consider pigments. Roman concrete tends to dominate material discussions because it involves giant surviving structures and therefore behaves in a suitably dramatic fashion. But some ancient pigments and surface treatments raise similar questions. Egyptian blue, for example, was one of the earliest synthetic pigments. It was not dug from the ground in finished form. It was manufactured through controlled heating of silica, copper compounds, calcium, and an alkali source. That alone should already make it clear that ancient makers were not limited to merely using raw nature as found. They were capable of transformation. They could manipulate ingredients, temperature, and process to generate new materials with durable optical properties. The same goes for famous ancient paints and plasters that have lasted under conditions where one might reasonably expect them to have surrendered long ago. Frescoes, polished wall coatings, stuccos, coloured surfaces, and floor materials survive not because age is kind, but because the original materials and applications were often good. Lime plasters can become extraordinarily durable when prepared and applied well. Polished finishes do not happen because workers were in a cheerful mood and rubbed at random. They happen because a civilization knows how long to slake lime, how to prepare aggregates, how to apply layers, how moisture affects curing, and how to finish a surface so it behaves as intended. Even glass deserves a mention here, because ancient glassmaking is another field where practical control exceeded what many modern people assume. Producing glass requires careful temperature management, composition knowledge, colour control, and forming skill. Ancient glassmakers across the Mediterranean, Near East and elsewhere were not just producing curiosities. They were making vessels, decorative pieces, windows in some contexts, and coloured materials at substantial levels of refinement. The chemistry was not articulated in modern terms, but it was no less real for that. A successful glass workshop does not emerge from ignorance. It emerges from generations of getting the melt wrong until eventually people become very good at getting it right. And then there are materials that survive mainly by making archaeologists quietly grateful and everyone else somewhat confused. Certain mortars, for instance, continue to perform well after centuries because the lime, aggregate, particle size, mixing, application, and curing conditions were all understood well enough by the people who used them. Traditional hydraulic mortars, pozzolanic mixes, earth and plasters stabilised in clever ways, and fired ceramic building components all reveal forms of knowledge that were empirical, place-based, and often highly optimised. Again, not magical, not beyond science. Just science practiced through making rather than through publication. This is where modern comparisons become especially awkward, because we often assume superior knowledge should mean universal replacement. If ancient materials were so good, why did they disappear? The answer is usually the same one that explains much of history, because durability is not the only thing societies optimise for. Cost matters, labour matters, speed matters, available ingredients matter, transport matters, political collapse matters, supply chains matter. A material system that performs brilliantly in one empire with one set of quarries, kilns, labour arrangements, and building goals may not survive the transition into another era with different incentives. Once continuity breaks, even excellent materials can fade from common use. Roman concrete again provides a very simple example of this. It is not enough to know that volcanic ash plus lime plus aggregate can produce useful results. You need access to the right ash or suitable analogues. You need traditions of use. You need the wider construction culture that makes such material attractive and practical. If later builders shift toward brick, stone reuse, different mortar systems, timber or other forms more suited to their economic and political world, then the exact old material regime weakens. A few texts survive. A few structures survive. The full culture of use does not. Centuries later, modern researchers peer into a harbour wall and begin acting as though the Romans were mischievously withholding trade secrets from the future, when in reality, their civilization simply stopped being there to keep teaching its builders. The same is true in metallurgy. When all sources change, charcoal becomes scarce, trade routes are disrupted, imperial systems collapse, or military demand shifts, entire metallurgical traditions can shrink or fragment. Knowledge becomes more local, then more patchy, then partially lost. Some practices survive in craft pockets, others vanish. Modern efforts to recreate old materials sometimes discover, rather rudely, that the historical object depended on conditions not easily reproduced in an industrial setting designed for different outputs. The old material was not better in every way. It was embedded in a world that knew how to make that exact thing well. There is also a philosophical difference worth noticing. Ancient builders often worked with the expectation that structures should last a very long time, sometimes effectively forever in symbolic terms. Not every ordinary house, of course. Ancient people were perfectly capable of building temporary things when temporary things were enough. But monumental and infrastructural works could be conceived under a horizon of endurance that modern construction does not always share. We build plenty of things now with long service lives in mind, but we also build much that is optimized for cost, speed, replaceability, maintenance cycles, regulatory convenience, and acceptable lifespan rather than near permanence. If a Roman engineer and a modern developer sat down together, they would likely agree about some structural basics, and then disagree profoundly about why anyone should spend that much time making a harbour wall difficult to kill. This does not make ancient people nobler. It just means their incentive structures could be very different. A state, empire, temple complex or ruling elite that wanted to advertise permanence in stone, concrete and metal might be willing to invest in material solutions that are expensive in labour and slow in execution. Under those conditions, craftsmen refine methods, repetition improves outcomes, materials are tested by use, not by short-term projections. Over time, a civilization develops a body of practical material science, whether it uses that phrase or not. And that phrase, practical material science, is really the heart of the matter. Ancient civilizations did not need electron microscopes to learn that some ashes improve mortar, some sands behave better than others, some firing temperatures strengthen ceramics, some ores produce superior metal, some heat cycles produce stronger blades, some surface treatments preserve, some pigments hold colour, and some mixtures survive water better than others. They learned through contact, failure, memory and repetition. That is slower than modern lab work, certainly. It is also, when sustained for centuries, surprisingly powerful. Which is why so many of these materials still feel difficult to match exactly. Not because the ancients transcended chemistry, but because they participated in it so intimately through long traditions of making that the resulting products were shaped by environments and craft cultures modern industry does not automatically reproduce. We can imitate, we can analyse. In many cases we can come close or even improve in selected ways. But exact recovery is another matter. Exact recovery asks us not only to copy ingredients, but to recover process, context, and intention, which is often where the real difficulty begins. And perhaps the most inconvenient lesson in all this is that materials do not become impressive only when they are flashy. Some of the most successful ancient substances look plain. Concrete looks plain until it survives the sea. Mortar looks plain until it holds a wall for a millennium. Steel looks plain until you understand the furnace logic behind it. A plaster surface looks plain until it remains coherent after centuries of weather. Ancient civilizations were often better than we expect at turning ordinary ingredients into stubbornly durable matter. Lime, ash, sand, ore, fuel, clay, stone. Nothing there sounds like a miracle. The miracle, if one insists on the word, is organisation. Organisation of heat, ingredients, labour, patience, and repeated correction, until matter begins behaving in a reliable way. And once matter becomes reliable, architecture can become more ambitious. Domes become possible, harbours become possible. Long-lasting vaults, baths, reservoirs, floors, road systems, blades, fittings, decorative programs, and structural systems all become possible. Materials are not a side topic. They are the quiet permission behind the rest of the built world. Ancient builders could dare larger, higher, wetter, heavier, and more permanent works because they trusted what their substances would do. That trust had to be earned. It was earned in kilns, furnaces, quarries, workshops, and job sites over generations. And once you begin to see that, another question becomes hard to avoid. Because knowing how to make durable materials is one thing, but getting those materials, along with all the giant stones and building elements that depended on them, into the right place is another. However clever the concrete, however refined the metal, however durable the mortar, none of it removes the old and very physical problem that ancient civilizations kept solving with alarming seriousness, which is how to move what seems too heavy to move at all. At some point, every conversation about ancient construction runs straight into the same stubborn question. Fine. Perhaps they understood stone. Fine. Perhaps they knew how to survey land, manage water, shape hard materials, and organise labour better than we casually assume. But how exactly did they move the things that seem too heavy to move at all? That is usually the moment when admiration turns into a practical headache. Because it is one thing to stand in front of a massive block already resting in place and call it impressive. it is another to picture that same block before it arrived, still in the quarry or lying awkwardly somewhere along a route, waiting for a human society without modern cranes, diesel trucks, or hydraulic systems to do something about it. And this is where people tend to split into two camps. One says the answer must be simple, that enough people pulling hard can solve nearly any problem, and that ancient transport was basically a very large and very sweaty version of moving furniture with your friends, except the furniture weighed 50 tons, and the friends were somewhat less free to decline. The other says the answer must be unknowable, or nearly magical, because the scale looks intolerable to common sense. As usual, both positions miss what makes the subject interesting. Ancient people were not solving these problems with either casual ease or supernatural tricks. They were solving them with planning, terrain management, leverage, friction control, staging, timing, and large numbers of people working in ways that had to be far more organised than the word manpower alone suggests. That last part matters, because manpower is often treated like an explanation when really it is only a resource. Saying that many workers moved a giant stone is a bit like saying many ingredients made a good meal. It is true, but it leaves out everything that makes success possible. What arrangement did the workers use? What were they pulling? Over what surface? At what gradient? With what rest points? Under whose instruction? With what tools to keep the load from shifting, sinking, twisting, or running away in precisely the direction least helpful to everyone involved? Ancient transport was never just about force, it was about controlled force. That is the difference between moving a monument and creating an accident memorable enough to survive in oral tradition for generations. The quarry is the right place to begin, because moving a great stone starts before the stone is fully free. Once a civilization commits to using massive blocks or monoliths, the first challenge is detachment. The stone has to come away in a shape worth keeping. That means identifying a workable seam or bed, cutting channels, using wedges, exploiting natural fracture lines where possible, and avoiding cracks that will turn several months of effort into a very expensive lesson. This alone required a lot of judgment. Quarries are full of silent evidence that ancient builders were thinking constantly about how material behaves under force. They were not just hacking away until something large happened to come loose. They had to release the block while preserving the block, which is a much more delicate idea than the word quarrying makes it sound. Once detached, the stone becomes a transport problem, and transport begins with reducing unnecessary friction while maintaining control. Modern people often picture rollers first because rollers are intuitive. Put round things under heavy things, and perhaps the universe will become cooperative. Sometimes that likely helped. In certain conditions, on prepared ground, with moderate gradients and careful management, rollers can be useful. But they are not a universal answer, and giant loads can make them awkward, unstable, or inconvenient depending on terrain and the shape of the object. Sledges, by contrast, appear in many plausible reconstructions because they spread the load and can move over prepared surfaces more predictably. A sledge dragged over wetted ground, compacted earth, wooden tracks, or specially prepared paths becomes much more manageable than a block dragged directly across raw terrain, as if everyone involved had simply lost an argument with a hillside. Ancient Egyptian evidence is especially helpful here because it gives us both monuments and glimpses of process. One famous tomb painting shows a colossal statue being hauled on a sledge by a large crew, while a worker at the front appears to be pouring liquid, often interpreted as water, onto the path. This is not a minor detail. Wetting sand or prepared ground can significantly reduce friction under the right conditions, allowing a heavy load to move more efficiently and with better control. It is one of those wonderfully irritating examples of ancient practicality. The method is not glamorous. It does not satisfy people who want secret machines or lost powers, but it is exactly the sort of grounded physical intelligence that ancient labour systems would have relied on. A better surface means a better chance of moving the load without everyone involved quietly reconsidering their life choices. This also reminds us that route preparation mattered at least as much as hauling. A giant stone is not just moved through space. Space must be made ready for the stone. Ground may need levelling. Slopes may need cutting, filling, or reinforcement. Soft spots have to be managed. Sharp turns become a serious concern. Bridges may be impossible, requiring alternate paths. Seasonal timing matters, especially if frozen ground, damp conditions, or river levels can be used advantageously. A civilization moving heavy material repeatedly would not treat the path as an afterthought. The path was part of the machine. That idea that the landscape itself became part of the transport system is one of the most useful ways to think about ancient heavy movement. We tend to focus on the object because the object is dramatic, but a stone can only be moved if many other things are made ready first. Roads are improved or temporarily prepared. Ramps are built. Embankments are raised. Timber is gathered. Ropes are produced. Work crews are arranged in teams. Resting stations may be established. Coordinating signals have to be understood. In some cases, canals or river barges become part of the solution, which is especially important in Egypt, where the Nile offered a transport corridor that could drastically reduce the amount of overland hauling required for certain materials. Water transport changes the problem, though not by making it trivial. Getting a massive block onto a boat or barge, securing it, floating it safely, then unloading it again simply relocates the difficulty. It does not remove it. Still, rivers and canals were an enormous advantage wherever they could be used. Ancient societies understood this perfectly well. Heavy transport by water is almost always preferable when available, because water carries weight in a way land makes you negotiate block by block and metre by metre. Egyptian building campaigns made extensive use of river systems to move stone from quarries to construction zones. Roman builders did the same whenever possible. So did other civilizations with access to suitable waterways. This is not evidence of convenience, it is evidence of intelligence. The best heavy lifting strategy is often not lifting at all, at least not on land, if the current and buoyancy can be persuaded to help. But of course not every monument sits obligingly beside a navigable river, and even when water transport is possible, the final approach is usually overland and often upward. That is where ramps enter the discussion, and ramps have generated both serious research and an almost comical amount of popular oversimplification. People say ancient builders used ramps as if that were the end of the matter, when in reality the phrase leaves almost every useful question unanswered. What kind of ramp? Straight, zigzagging, wrapping, internal, external, temporary, staged? Built of what? Earth, rubble, brick, timber reinforcement? At what slope? Wide enough for what sort of traffic? Maintained how? Removed when? How is the surface stabilised under repeated heavy passage? A ramp is not one thing. It is an entire family of engineered compromises between gravity, material availability, labour input, and the dimensions of the load. This is why the debate over pyramid construction remains lively, even when many broad principles are widely accepted. The question is not whether ramps played a role. They almost certainly did in some form. The question is which forms were used at different stages and how those systems interacted with labour, space, and the growing monument itself. For lower courses, broader and more direct ramp systems may be plausible. As height increases, the ramp problem becomes more severe. A shallow enough slope for safe heavy hauling requires enormous ramp volume, which itself becomes a construction project of almost ridiculous scale. That has led scholars to explore combinations of external ramps, internal passage strategies, levering methods, and stage-by-stage adaptations. None of this suggests confusion about whether ancient people could move blocks. It suggests that moving blocks to increasing height is a hard enough problem that one simple answer rarely satisfies every constraint. And that really is the pattern across the ancient world. There was probably no single universal method. Different loads, terrains, cultures, and materials demanded different solutions. A granite obelisk in Egypt is not the same problem as a limestone block for a pyramid core. A monolith at Baalbek is not the same problem as the shaped stones of an Inca wall. A carved column drum, a bronze statue component, a timber beam, and a basalt stela each create different headaches. Ancient transport systems were flexible because they had to be. They combined hauling, sledging, levering, earthen works, water transport, temporary supports, and repeated small adjustments. Leverage deserves special attention because it is one of the oldest and most powerful ways humans make large objects behave a little more reasonably. A heavy stone does not need to be lifted fully in one clean theatrical motion. In fact, trying to do that is an excellent way to discover new forms of regret. It can be raised incrementally. One side is lifted slightly, packing inserted beneath, then another side, then more packing, more lifting, more cribbing, more adjustment. Over time, what seems impossible in one act becomes possible through many smaller acts. This is how many difficult transport and placement operations likely became manageable. Not through one grand gesture of strength, but through a sequence of controlled nudges, supports, and resets. Ancient builders did not always need to conquer gravity. They needed to negotiate with it patiently. The placement of standing stones or obelisks likely depended on similar logic. Raising a monolith upright is not merely hauling in a different direction. It is a choreographed transfer of weight and balance. Pits, earthen embankments, ropes, wooden frames, counterweights, and controlled lowering into prepared sockets may all have played roles depending on the case. If that sounds complicated, it is because it is. Yet complexity should not be mistaken for impossibility. Ancient people were perfectly capable of devising processes where the most dangerous phase of movement was broken into safer, more manageable steps. A society that can build a giant stone object usually also understands that dropping it at the end would be unpopular. There is another factor modern people sometimes underestimate, and that is rhythm. Large teams can accomplish astonishing things when their effort is coordinated. Pulling must happen together. Adjustments must be timed. Commands must be heard. Rest periods matter. Uneven force can twist a load, snap a rope, or turn a stable drag into a diagonal disaster. This implies not only manpower but leadership at very local levels. Foremen or crew leaders had to control pace, sequence and safety as much as any ancient labour culture allowed. It also implies experience. A team that has moved heavy loads before is not the same as a crowd pushed into the same direction for the first time. Practice changes efficiency. Repetition changes judgment. The first giant block a society moves is a harder teacher than the 10th. That point often gets lost because we look at surviving monuments as isolated spectacles, rather than the end products of repeated systems. A culture that builds in a large stone does not begin from zero each time. Quarry crews learn, hauling crews learn, road makers learn, surveyors learn. The state or temple administration learns how much food, rope, timber, and time a transport operation consumes. Mistakes become lessons. Successful routes become precedents. Over generations, what once required experimentation becomes standard practice within that civilization's limits. We may not know every command shouted on the work path, but we can be fairly sure the people involved were not reinventing heavy transport from first principles every morning. This is especially important in discussing sites like Baalbek, where the stones are so large that modern viewers often react by deciding the answer must lie outside normal human capabilities. It does not. It lies inside normal human capabilities organised on an extraordinary scale. That does not make the problem simple. It makes the people solving it more impressive. The larger the monolith, the less room there is for casual explanation. But the same broad toolkit still applies. Detachment, preparation, route engineering, friction reduction, staged movement, leverage, careful bedding, and huge amounts of labour directed with precision. One may still argue over exactly which combination of methods was used in each case. That is healthy. But the existence of multiple plausible families of technique is itself a sign that ancient engineering belongs to the realm of difficult reality, not fantasy. The Inca world provides another useful perspective because in the Andes the challenge of transport collides with terrain that seems almost deliberately insulting. Steep slopes, high altitudes, narrow paths, variable weather and difficult footing are not what most people would choose for large stone architecture if easier options were available. Yet Inca and pre-Inca builders moved and fitted substantial stones in precisely these conditions. That alone should warn us against overly neat models. Ancient transport did not always occur on idealized flat ground, with obedient weather and abundant timber. Sometimes it took place where every metre had to be argued from the mountain. In such contexts, smaller incremental movement, carefully prepared surfaces, local leverage, and team coordination may have mattered even more than grand hauling systems. The stone does not need to travel in a straight line to be moved successfully. It needs to travel in a controlled one. And then there is the problem of scale, not in single stones, but in total volume. It is easy to focus on a giant monolith because it is dramatic and numerically satisfying in a way historians sometimes learn to regret. But some ancient achievements are just as impressive because of the cumulative quantity moved. Millions of blocks in pyramid construction, vast amounts of fill and stone in platform construction, endless loads for terrace systems, roads, walls, canals and temple precincts. A civilization does not need one legendary stone to prove transport competence. It can prove it through repetition, through the fact that enormous material totals reach the right places over years or decades without the whole enterprise collapsing into administrative comedy. This is where logistics becomes the true giant hidden behind the giant stone. Moving heavy material requires food for workers, tool repair, rope production, path maintenance, supervision, scheduling, and often the synchronization of quarry output with transport capacity and construction readiness. If the site is not ready, transported stone becomes clutter. If the stone arrives too slowly, work crews idle. If the route breaks down, everything stops. Ancient monumental societies solved these problems not once but often repeatedly, and that organisational achievement is part of what we should mean when we say they moved what we can barely lift. The lift was only the final visible part of a much larger system. Modern experiments in experimental archaeology have been quite useful here. Groups using replicas or approximations of ancient tools and methods have shown again and again that surprisingly large loads can be moved with simple equipment, enough people, and well-prepared surfaces. None of this proves one exact historical method in every case, but it does something more valuable. It resets the imagination. It demonstrates that a load which looks impossible to a modern individual standing alone in a museum or at a site may become possible when approached as an engineering sequence rather than an isolated act of strength. That distinction is everything. Ancient builders were not lone heroes. They were collective problem solvers. There is also something worth saying about fear, because giant transport is terrifying in a practical sense. One badly controlled descent, one failed support, one snapped line, one unstable ramp section, one badly judged pivot point. The danger was real, and real danger tends to produce better procedural discipline than modern audiences sometimes imagine. Ancient crews moving colossal stones were not merely demonstrating power, they were surviving risk. That risk would have encouraged systems of caution, staging, checking and command whether or not those systems were written down. A civilization that repeatedly moved very heavy objects without constantly destroying them must have learned the value of not being stupid around mass. And perhaps that is the clearest answer to the old question. How did they move what we can barely lift? Not by defying physics, but by respecting physics so thoroughly that they found workable paths through it. They used the landscape, they used water, they used ramps, sledges, leverage, ropes, packing, teams, and time. They made small gains accumulate. They turned enormous tasks into sequences of manageable ones. They accepted slowness where slowness prevented failure. They invested labour not only in the object but in the route and the support system around the object. They did not ask whether one person could lift it. They asked how a whole society could make lifting unnecessary, dragging feasible, and final placement controlled. That answer is less cinematic than secret machinery, but it is much more demanding. It requires us to admit that ancient civilizations could be astonishingly good at practical coordination. They could spend years preparing for a movement modern people expect to happen in an afternoon. They could devote manpower on a scale modern economies rarely tolerate. They could bind engineering, labour and authority together tightly enough that enormous material movement became not a miracle, but a state function. And once you grant them that, something else becomes unavoidable. The ancient world stops looking impossible and starts looking underappreciated, which is usually the point where myths begin to lose their charm and the real achievement becomes much harder to dismiss. Once you start taking ancient engineering seriously, a different problem appears almost immediately. The structures become harder to ignore, but they also become harder for people to fit neatly into the stories they already like telling. Some of those stories are romantic, some are dismissive, some are theatrical enough to sell books, television specials, and very confident internet videos made by people who have never once tried to move a damp sofa up a staircase, let alone a 70-ton stone across uneven ground. But they all tend to circle the same discomfort. If ancient civilizations were capable of this much, then the old picture of the past as crude, confused, and mostly waiting for modern intelligence to arrive begins to look flimsy. And when familiar pictures grow flimsy, theories rush in to fill the gap. This is where the conversation becomes less about stones and more about modern imagination. Because the trouble with underestimating the past is not just that it produces bad history, it produces bad explanations. The moment people decide ancient builders could not possibly have achieved something on human terms, they begin looking for other options. Maybe a lost super-civilization taught them. Maybe outsiders did it for them. Maybe secret tools existed and then vanished without leaving a trace. Maybe aliens descended, assessed the local masonry situation, and got involved for reasons that remain oddly selective and architecturally specific. The details change. The pattern does not. First, real human skill is discounted. Then impossible explanations become emotionally attractive because they feel easier than admitting ancient people were more capable than expected. That pattern is worth slowing down over because it tells us something important about how myths are made. Myths do not always appear because evidence is absent. Often they appear because evidence is inconvenient. A giant stone in place is evidence. A precisely aligned monument is evidence. A durable material is evidence. A mountain city with sophisticated water management is evidence. But evidence like that demands a serious response. It asks for logistics, labour organisation, geology, hydrology, craft traditions, astronomy, political power, and administrative continuity. Those are not flashy answers. They are difficult answers. They require patience. By contrast, a myth can explain everything in one smooth gesture. Too smooth, usually. Mystery is compressed into a single dramatic cause, and all the hard work of thinking disappears. This is why ancient monuments are so often recruited into narratives that say more about us than about the people who built them. The ancient astronaut idea is the most obvious example, but it is really just one branch of a larger habit. The habit is treating unfamiliar competence as evidence of external intervention. That habit has a long history and it has not always been innocent. In many cases, it overlaps with older colonial and racial assumptions about which civilizations were supposed to be intelligent, inventive, and capable of engineering excellence. When a monument in Europe is impressive, people often begin by assuming the builders were clever. When a monument elsewhere is impressive, some people become strangely eager to search for vanished teachers, outside help, or hidden civilizations that can absorb the credit. It is a deeply revealing double standard and not a flattering one. That does not mean every strange theory is motivated by prejudice in a conscious sense. Many people are drawn to them for simpler reasons. They like wonder. They like feeling that the world still contains secrets large enough to resist dry explanation. They are bored by bureaucracies and thrilled by lost technologies. They hear the phrase, "we do not know exactly how," and translate it into, "therefore no ordinary explanation can exist." It is a very human leap, also a very sloppy one. Uncertainty about specific procedural details is not evidence that basic human capability has failed. Archaeologists debate methods because methods matter. The existence of debate is not a sign that history has reached a supernatural cliff edge, and yet the cliff edge remains popular because modern people are often not very good at appreciating the scale of ordinary collective effort. We understand spectacular technology more easily than disciplined coordination. If someone shows us a crane lifting a large object, we accept it because the machine looks powerful. If someone explains that thousands of workers, organised well, using sledges, ramps, ropes, water transport, levers, and carefully prepared routes could move the same object, many people become sceptical. Which is odd, because the second explanation, difficult though it is, rests on known physical principles and known human capacities. But it feels less intuitive because modern life hides large-scale labour organisation from most people. We see machines and assume machines are the only serious form of strength. This weakens historical imagination in a very particular way. It makes ancient solutions look impossible, not because they violated physics, but because they relied on social and material conditions unfamiliar to us. An ancient state could mobilise labour for years or decades toward a monument tied to religion, kingship, defence, or prestige. It could train specialised craftsmen within stable traditions. It could extract resources, standardise duties, coordinate transport, and normalise slowness in a way modern systems often resist. If we fail to picture that world clearly, the resulting monument starts to feel detached from human process, and once that detachment sets in, myth has an opening. There is another reason myths thrive, and it has to do with our strange relationship to evidence. People often say they want explanations, but what many really want is certainty delivered with confidence. Ancient history does not always cooperate. It gives us partial texts, damaged sites, modified structures, unfinished works, tool marks, residues, logistics we can model but not fully observe, and cultural meanings that have to be interpreted with care. This is how serious knowledge usually works. It accumulates through probabilities, converging lines of evidence, tested hypotheses, and revised conclusions. Myth, by contrast, arrives fully dressed. It never says perhaps when it can say obviously. It never pauses to distinguish between plausible, possible, and proven. That style is emotionally efficient. It is also one reason it spreads so easily. Take the common claim that certain stones are so perfectly fitted they must have been machine cut by unknown advanced devices. The first problem is usually descriptive. Perfectly fitted often means very well fitted, sometimes after weathering, restoration, selective photography, or a failure to inspect the full site. The second problem is conceptual. Good fit does not require secret machines. It requires patient shaping, repeated testing, abrasion, and skilled judgment. The third problem is cultural. Once one decides that high-quality stonework cannot come from ancient craftspeople, one has already lost the argument before it begins, because the conclusion was built into the disbelief from the start. The same thing happens with claims about impossible alignments, impossible weights, impossible materials, impossible drilling, impossible polishing, impossible transport. Impossible is one of the laziest words in this whole discussion. Very difficult, yes. Labour-intensive, yes. Requiring a sophisticated state or strong workshop tradition, yes. Poorly documented in exact step-by-step detail, often yes. But impossible generally means only that the speaker has not accepted the scale of ancient discipline required. It says less about the structure than about the limits of the observer's imagination. This is where the phrase underestimating the past becomes especially important. The past is not underestimated only by people who sneer at it openly. It is also underestimated by people who praise ancient monuments extravagantly while quietly assuming no ordinary human beings could have made them. That sounds like admiration, but it is really another form of refusal. It refuses to take ancient labour, intelligence and organisation seriously enough to let them remain human. The builders are either made primitive and clumsy or elevated into something nearly magical. In both cases, the real people disappear, and the real people are the point. Builders who knew stone, surveyors who knew land and sky, metal workers who knew furnaces, plasterers who knew mixtures by feel, quarry workers who could hear stress in rock, administrators who knew how much grain, rope and time a project would consume, priests and rulers who attached political or sacred meaning to orientation, durability and monumentality, work crews that learned from previous campaigns, apprentices who absorbed techniques not from abstract theories, but from correction, repetition, and direct contact with material. Once these people come back into view, the monuments stop looking like impossible interruptions in history and start looking like the visible output of entire civilizations operating at high competence. This does not remove every mystery, and it should not. Some exact methods remain uncertain. Some sites preserve too little evidence to settle every dispute. Some achievements still feel astonishing, even after plausible engineering models are laid out in front of us. Astonishment is not the enemy of good history. In fact, it is often the beginning of it. The problem comes when astonishment hardens into laziness, when that is amazing turns too quickly into therefore it cannot have been done by those people. That leap is where myth begins doing damage, and the damage is not only factual, it reshapes how people understand civilization itself. If ancient achievements are always explained away as outside intervention, then human societies lose credit for one of their most important traits: the ability to become extraordinarily good at difficult things through continuity, training and collective effort. The lesson of ancient engineering is not that humans need rescuing by superior beings. The lesson is that humans, under certain conditions, can coordinate knowledge and labour to an almost uncomfortable degree. That lesson is more useful and more humbling than any fantasy about lost machines. There is also an irony here that deserves notice. Many modern myths about ancient technology come from societies that pride themselves on rationality and progress. Yet those myths often reveal a very poor understanding of how real engineering works. Real engineering is rarely elegant in the storybook sense. It is repetitive, conditional, improvised within limits, and supported by vast amounts of background labour. It depends on supply chains, maintenance, staging, friction, weather tolerances and compromises so unglamorous that they're usually left out of documentaries. Ancient engineering was no different. If anything, it was more entangled with labour and environment. Myth strips all that away and replaces it with a single miracle cause, which is not a higher form of explanation. It is just less work. This is why responsible archaeology can sometimes sound less exciting than speculation, while actually being more impressive. When archaeologists say, in effect, here is the quarry evidence, here are the tool marks, here are the transport traces, here are the labour settlements, here are the experimental results, and here are the remaining uncertainties. They are not draining wonder out of the past, they are anchoring wonder to reality. That reality includes failed attempts, abandoned stones, modifications, repairs, regional variation, political constraints, changing building traditions, and evidence of people learning over time. A monument built by real humans inside real institutions is not less impressive than a monument built by imaginary super beings. It is more impressive because it means the capacity existed in ordinary human history all along. There is another practical problem with myths. Once they become popular enough, they begin to distort what questions get asked. Instead of asking how a wall behaves in an earthquake, people ask what secret beam cut the stones. Instead of asking how a society organised water in an arid trade centre, they ask what vanished civilization left clues behind. Instead of studying ancient metallurgy through ore sources, furnace reconstructions, slag analysis and thermal practice, they ask why modern science cannot explain it, usually while ignoring the scientists who are actively explaining it. Bad theories do not just fail on their own terms, they pull attention away from the real achievements, and those real achievements are often more interesting than the myths, because they reveal a broader picture of civilization. Ancient monuments were not isolated spectacles made for future tourists. They were products of economies, belief systems, ecological adaptations, labour regimes, and craft traditions. To understand them properly means understanding the societies behind them, including the uncomfortable parts. States that could mobilise vast labour could also exploit. Monumental ambition often sat beside harsh hierarchy. Trade wealth could finance beauty and coercion at the same time. The real past is richer and less flattering than fantasy. It contains both genius and brutality, which is exactly why it deserves serious attention. This also helps explain why some myths remain emotionally persistent, even after evidence piles up against them. The myth is simpler, cleaner, and often morally easier. It avoids the mess of ancient politics, labour systems, and human complexity. It turns a monument into a puzzle box rather than a social product. And because puzzle boxes are entertaining, people defend them long after the evidence has moved on. The result is that ancient civilizations, already distant from us in time, become distant in another sense too. They are treated as backgrounds for mysteries instead of as historical actors in their own right. There is a related myth on the other side as well, and it deserves criticism too. This is the myth that ancient people were basically like us but worse at everything, until the industrial age began correcting the situation. This version sounds more sober because it avoids aliens and hidden empires, but it carries its own distortions. It underestimates how deep craft traditions could become. It underestimates how much can be achieved with non-industrial tools when labour is abundant and methods are refined. It underestimates the intelligence embedded in practical systems of observation. Most of all, it underestimates the possibility that some forms of knowledge can be lost, not because later people are foolish, but because historical conditions change. That last point is worth holding on to. The past was not a single ladder of increasing competence. Some things improved dramatically, others were forgotten, replaced, or rendered uneconomical. Some materials changed because new priorities made different compromises more attractive. Some building traditions vanished when the institutions supporting them collapsed. Some techniques survived only in fragments. The trouble with simplistic theories, whether mystical or dismissive, is that they flatten all this unevenness. They assume history must move in one direction, and that anything hard to explain must belong outside ordinary human development. The built record says otherwise. If anything, ancient monuments teach a more demanding lesson. Human capability is broad, but it is also conditional. Civilizations become capable through continuity, social organization, environment-specific knowledge, and the training of specialists over long periods. Remove those supports and capability can contract. Change the incentives, and it can shift direction. That is why some ancient works remain hard to replicate exactly. Not because we are inferior, and not because they were magical, but because we inhabit different systems with different goals. Once that is understood, the old monuments stop being arguments against modernity or excuses for fantasy. They become evidence that history contains more variety and competence than simple stories allow. And perhaps that is the deepest trouble with underestimating the past. It makes the present look flatter too. If we imagine ancient people as dim, then modern people get to feel clever without doing much. If we imagine ancient achievements as supernatural, then modern people get to feel exempt from serious comparison. In both cases, we avoid the harder conclusion, which is that human beings have long been capable of astonishing things when knowledge, labour, patience, and purpose converge. That conclusion is harder because it leaves us with no one else to credit and no one else to blame. The builders were real, Their societies were real, their tools were limited but effective, their methods were demanding, their results were extraordinary. We do not need a myth to make that interesting. So when strange theories gather around ancient monuments, the best response is not annoyance alone, though some annoyance is understandable. The best response is to ask what those theories are trying to avoid. Usually they are avoiding effort. The effort required to imagine ancient labour at scale, to respect craft traditions, to accept incomplete evidence without panicking, to distinguish uncertainty from impossibility, and to let real human civilizations be as capable as the monuments suggest. Once that effort is made, the myths begin to lose their grip. What remains is not a diminished world, but a fuller one. A world in which the past is neither primitive nor magical, but serious. Serious enough to have built things that still force us to think carefully, argue honestly, and lower our voices a little when we stand beside them. And once the myths begin to clear, something else becomes possible. The monuments stop being problems to explain away and start becoming teachers again, not because they contain hidden prophecies or secret machines, but because they reveal what disciplined societies can do when they decide that durability, precision, and effort matter more than haste. That is a much better lesson to carry forward, especially when the question is no longer whether the past was capable, but what exactly those old builders still have to say to a modern world that often mistakes speed for mastery. So after all of this stone, dust, weight, geometry, labour, astronomy, hydraulics, carving, hauling, fitting, and the very old human habit of leaving behind objects large enough to make future generations feel slightly inadequate, what do these ancient civilizations actually teach us? Not just about the past, but about us, about what people are capable of, about the range of human possibility when enough attention, discipline and purpose are gathered in one place, for long enough that even the landscape begins to take notice. The first lesson is probably the simplest, though for modern people it can be strangely hard to accept. Human beings do not need to be modern to be intelligent. That sounds obvious when stated plainly, yet an astonishing amount of public thinking behaves as if it were controversial. We still slip so easily into the idea that the past was full of half-formed societies, fumbling through trial and error until eventually the present arrived and everything became properly clever. But old monuments resist that story, not because they prove ancient people knew everything. Clearly they did not. No civilization ever has. They prove something more interesting. They prove that intelligence takes many forms, and that some of those forms become almost invisible to later societies if they are not packaged in familiar modern ways. A builder who understands how a wall settles, how a slope fails, how a stone fractures, how a joint locks, how water eats through a badly planned channel, how sunlight enters a space at a certain time of year, and how to organize teams so that none of those things go wrong at once, is not less intelligent because he does not express that knowledge in the language of modern engineering software. He is intelligent in a way his world taught him to be. And if enough people in that world share, refine, and transmit those forms of intelligence, then the results can become enormous. This is perhaps the oldest mistake modern arrogance still makes. It assumes that knowledge only counts if it looks like our knowledge. Ancient civilizations remind us that skill can be embodied, local, practical, cumulative, and still reach astonishing heights. A mason does not need to explain mineral structure at a conference to know which stone will betray him. A water engineer does not need a computerized simulation to understand the slope a channel requires after a lifetime of watching flow. A temple planner does not need a telescope to know where the solstice sun will rise if generations have been paying attention. The past teaches that disciplined observation, stored socially and repeated faithfully, can produce results of lasting consequence. It also teaches something that modern culture rarely likes to hear, which is that patience is not just a virtue, it is a technology. Ancient civilizations built as though time itself were available for use. Not unlimited time, of course. Even emperors, kings, priests and city councils eventually run into mortality and budgetary irritation. But many ancient societies were willing to think in longer durations than modern systems usually reward. A structure might take decades. A terrace network might require generational maintenance. A carved sanctuary might unfold through long stages. A road system might outlive the political power that first organised it. They built under horizons of time that made slowness acceptable if slowness improved the result. Modern societies can still do this sometimes, but often only with difficulty. We are excellent at acceleration, less excellent at duration. We optimize for speed, efficiency, turnover, cost recovery, and visible short-term results. Ancient monumental building often belonged to another rhythm. It accepted laborious refinement, repeated correction, and extended commitment as the normal price of permanence. That does not mean the ancient world was wiser in every moral or political sense. Far from it. But it did understand that some achievements only become possible when haste is denied the right to make every decision. And that connects to another lesson, one far less romantic and much more important. Human possibility is collective long before it is individual. Ancient monuments are often discussed as though they were acts of isolated genius. A brilliant ruler, a visionary architect, a master builder whose exceptional mind somehow radiated order outward into stone. Real civilizations do not work like that. They work through accumulated competence. A monument rises because quarry workers, surveyors, tool makers, transport crews, planners, rope makers, water managers, masons, plasterers, and administrators all become part of the same process. No one pair of hands can make a city. No single mind can drag a monolith uphill. Ancient construction teaches that human possibility expands dramatically when societies learn how to coordinate specialized knowledge at scale. This is one of the most striking things the old world still says to us. Great works are not made only by inspiration. They are made by organization. The invisible achievement behind every visible monument is usually the same. A civilization found a way to align labor, skill, resources, and belief strongly enough that matter began to obey a shared plan. That may sound less glamorous than mystery, but it is actually much more profound. It means human beings do not become impressive only when they invent exotic machines. They become impressive when they build systems capable of carrying intelligence through many hands without losing the shape of the idea. And yet there is a warning built into that lesson too, because not all forms of collective ability are gentle. Ancient civilizations often achieved wonders through harsh hierarchies, concentrated power, seasonal obligations, coerced labor, and social systems modern people should not wish to imitate. It is important to say that plainly. Admiration for the engineering should not become nostalgia for the politics. A pyramid may be magnificent and still belong to a deeply unequal society. A city carved from rock may testify to astonishing coordination, and also to systems of extraction, command and sacrifice that came at a heavy human cost. The past teaches possibility, yes, but it also teaches that possibility is not the same as goodness. That is a hard but useful distinction. It means the old monuments should neither be worshipped uncritically nor explained away defensively. They should be read honestly. Human beings can do extraordinary things together. Those things can be beautiful, durable, and intellectually serious. They can also emerge from systems that are brutal, controlling, or deeply unjust. Ancient civilization teaches both truths at once. That may be one reason the built remains feel so powerful. They are not simple moral objects. They are evidence. Evidence of capacity, ambition, concentration, and the very old tendency for greatness and cruelty to inhabit neighbouring rooms in the same palace. Still, even with that caution in place, there is a more generous lesson worth holding on to. Ancient civilizations teach that adaptation is one of the highest forms of intelligence. They did not build in a blank world. They built in deserts, floodplains, mountains, forests, volcanic zones, coasts, and arid canyons. They built with the materials near them, the fuels they could gather, The soils they had to stabilize, the climates they had to endure, and the celestial rhythms they cared enough to track. The best ancient engineering is not impressive because it ignores environment. It is impressive because it reads environment closely and turns that reading into form. A Roman harbour is one answer to a coast. An Andean terrace is one answer to a mountain. An Abertian water system is one answer to desert volatility. An underground refuge city is one answer to insecurity and geology. A temple aligned to seasonal light is one answer to a world in which the sky carries meaning. These are not generic expressions of cleverness. They are local expressions of it. Ancient builders did not merely ask what they wanted to make. They asked what this place would permit, resist, reward, and punish. Modern civilization, for all its power, sometimes behaves as though place is an inconvenience to be overridden. The ancient world often had fewer illusions about that. That realism about place leads naturally to another lesson. Human possibility depends not only on invention, but on attention. The people who built the old monuments were often watchers before they were builders. They watched stone, they watched seasonal water, they watched stars, shadows, slopes, cracks, rainfall, drying times, and the performance of structures through years of weather. Knowledge grew from looking closely and looking repeatedly. It was patient, embodied, and often shared across generations. In a world that now swims in information while frequently starving for attention, that may be one of the most useful lessons of all. Attention sounds soft. It sounds almost decorative beside words like engineering and power. It is not soft. Attention is how one notices that a foundation shifts in only one corner. It is how one learns that a certain ash strengthens a mortar. It is how one sees the sun strike a chamber differently in winter than in summer. It is how one detects that a load moves more smoothly over wetted ground than dry. It is how one realizes that a hill slope can become productive if divided, retained, and drained correctly. Ancient civilizations often became formidable not because they possessed one miraculous secret, but because they trained enough people to keep noticing what reality was telling them. And that brings us to memory, which may be the quiet partner behind nearly everything ancient people built well. Memory in institutions, memory in craft traditions, memory in ritual calendars, memory in workshop habits, memory in the body, passed from teacher to apprentice until a process no longer needs explaining every time. We often talk about innovation as though it is the engine of civilization, and certainly innovation matters. But monuments remind us that continuity matters too. A technique becomes powerful when it does not have to be rediscovered from scratch in each generation. Ancient civilizations teach that one of the greatest forms of human possibility is not simply invention, but preservation of competence. That idea is more fragile than it sounds. Civilizations lose things, not just cities, dynasties and borders, but methods. Material traditions disappear, quarry knowledge breaks, recipes shift, ore sources vanish from use, apprenticeship chains fail, priorities change, skills once ordinary become mysterious. The old world teaches that progress is not guaranteed in every direction at once. Some knowledge accumulates, some knowledge scatters, some is replaced by better systems, some is abandoned for faster ones, some is forgotten until surviving structures embarrass later societies into paying attention again. If ancient monuments have a warning for us, it may be that capability is never safely stored forever. It must be practiced, taught, and valued, or it thins out very quickly. There is something oddly comforting in that too, though perhaps comforting is not quite the right word. It may be more accurate to say clarifying. Ancient civilizations remind us that human beings are not inherently shallow creatures living in a shallow age. We are capable of seriousness when our cultures make seriousness possible. We are capable of craft, endurance, and collective focus when those things are rewarded, supported, and taught. We are also capable of forgetting them. The built remains of the ancient world are therefore not only relics of lost greatness. They are evidence of what becomes possible, when a society trains itself toward depth rather than distraction. That may be why these sites still affect people so strongly, even when they know little of the technical details. A great wall, a pyramid, a carved sanctuary, a terrace landscape, a harbour structure, a road crossing difficult country, all of them give off the same feeling. Someone cared enough for long enough that the result escaped their own lifetime. That is a powerful thing to encounter now. We live among many things designed for turnover, replacement, and planned exhaustion. Ancient monuments, by contrast, often feel like arguments against temporary thinking. They say that humans can make things intended to outlast fashion, ideology, and administration. They say we are capable of durability not only in stone but in effort. Of course, there is a danger in letting this drift into sentimentalism. Ancient societies did not wake each morning full of serene purpose and begin placing well-cut blocks while discussing eternity over breakfast. They argued, governed badly, taxed heavily, conquered, misjudged, failed, and sometimes built monuments for reasons that were vain, fearful, or aggressively political. Human possibility includes pettiness on a grand scale too. But perhaps that makes the remaining lesson even more useful. We do not need ideal humans to produce extraordinary works. We need committed systems, skilled people, meaningful aims, and enough continuity for excellence to become normal. Ancient civilization is not proof that humans were once purer. It is proof that they were, as ever, complicated and still capable of astonishing discipline. And maybe discipline is the word that ties so much of this together. Not discipline in the narrow sense of obedience, though ancient states certainly valued that. Discipline in the broader sense of organized care. The ability to do difficult things correctly, repeatedly, over time, especially when no shortcut offers the same result. A fitted wall requires it, a durable concrete requires it, a long water channel requires it, a sky alignment requires it, a mountain city requires it. Ancient civilizations teach that human possibility is much larger than flashes of brilliance. It includes sustained exactness. It includes the humble miracle of doing the right thing again tomorrow. That is a lesson worth keeping, because it is so unfashionable. We like breakthroughs, we like genius, we like singular moments when history seems to leap. The ancient world reminds us that some of the most impressive leaps are really very long walks. Years of quarrying, decades of placement, generations of refining material, seasonal cycles of labour, continual correction, quiet maintenance. A civilization's highest achievements may rest less on sudden inspiration than on the ability to remain committed after inspiration has become ordinary work. That may be the most difficult form of possibility for any age to preserve. And if there is one final thing the ancient world still teaches, it may be humility, though not the timid sort. More the sturdy kind. The kind that allows us to admire the present without insulting the past. The kind that understands technology is not the only measure of seriousness. The kind that sees a surviving wall and does not ask, how could people without our machines do this? In a tone of disbelief, but asks instead, what kind of attention, organisation, and skill made this normal for them? That question is much more useful. It opens rather than closes. It lets the past remain human and still extraordinary. Because that, in the end, is what these civilizations give back to us if we let them. Not proof that modern life is worthless. Not proof that everything important has already been done. Not proof that lost ages were magical, and we have merely declined into poor taste and weaker mortar. They give us something better. They give us scale. They remind us that the human story is wider than our own habits. That people with different tools, different languages, different gods, different political systems, and different fears were still capable of reading stone, water, sky, and terrain with formidable intelligence. They remind us that possibility is often hidden inside ordinary materials until patience and coordination draw it out. They remind us that what looks impossible from a distance often becomes achievable when enough minds and hands learn how to work together without losing the plan. So the next time you see an ancient wall, or a carved cliff face, or the remnants of a road running off towards some horizon that no longer belongs to its builders, it may be worth pausing before the usual modern reflex arrives, before the quick assumption that we naturally know better because we came later. Later is not the same thing as deeper. Newer is not the same thing as wiser. More powerful is not always the same thing as more enduring. The old monuments do not ask us to envy the past. They ask us to take human beings seriously, across time, in all their complication. And perhaps that is the calmest, strongest thing they leave behind. Not a secret, not a prophecy, not an impossible machine hidden in stone. Just a very old reminder that people, when they gather skill, memory, attention, and purpose in the same place, can build far beyond what a casual age believes they should be able to, which is not only a lesson about them, it is rather inconveniently a lesson about us too.